everybody to the 2022 Summit on Drone Geophysics. This is the third summit on drone geophysics after 2 very successful years. Welcome all and thank you for attending. And I know we have participants from across the globe. So a special thank you to our sponsors of the summit. Their logos will be posted during the break, so you can take a look at that. Our platinum sponsors will do a 10-minute demonstration in between speaker talks. We'll have a platinum sponsor today and a second one on Thursday. So each presenter will have 15 minutes to present today and the remaining 4 days as well, 15-minute talks plus 5 minutes of Q&A. If the presenter's presentation goes into the Q&A, the session chair will ring a chime. So each day there'll be a different session chair, and an example of that chime is this bell here. So you'll know when you have, you'll have 1 minute left when you hear that chime. So that's 1 minute of your 20 minutes. So that means 1 minute left for questions. And the presenter should begin to wrap up at that time when they hear the bell. Whatever time is left over, we will use for Q&A so that we can ask presenters questions. And if you don't get to ask your presenter a question during the Q&A, or if they go over time, we do have a discussion at the end of each day planned. So that'll be an hour discussion at the end of each day, at which time we actually unmute everybody at that point and we can have questions then. So during the presentations today, everyone will be muted. So please type any questions you have in the Q&A box. And if time permits, we will get the questions to the speakers. During the discussion at the end of the day, everyone will then have the option to unmute, like I just said. Okay, so this year we're going to start the summit with an innovation panel. By using this time at the beginning of the summit, we all get to hear from some of the industry leaders who are paving the way for drone innovation. We can have a discussion to talk about some hot topics and challenges faced when using drones. So topics in this panel will include AI, so artificial intelligence, public perception of drones, beyond visual line of sight, and challenges when using drones for large-scale geophysical mapping. We'll also hear about some non-conventional platforms and sensors for UAVs and what is on the horizon. Other challenges faced by people in the drone industry are regulatory, so we'll bring this into the conversation as well. So the panel will be structured so that each panelist will have 2 questions, and we will also leave the Q&A box open for discussion during the panel. So after our panel, we'll have a 10-minute break and then come back for our platinum sponsor presentation. Yeah, so I think that's all the housekeeping. Just a quick introduction of myself and then followed by my co-chair, Callum. So my name is Laura Quigley and I'm a project geophysicist with Seequent. I'm based in Vancouver, Canada. I graduated with a master's in geophysics from the University of Toronto. I've traveled all over the world doing field geophysics, as well as spent several years doing geoscience research in Australia, in particular Brisbane. Over the past 2+ years, I've been training and supporting people to use Seequent software to process, plan, and interpret UAV magnetic surveys. My previous field geophysics experience includes processing airborne mag and EM data, as well as offshore seismic. So drones and geophysics are relatively new, and I find this to be very exciting and interesting. I never got a chance to use them in the field myself. So this is always exciting to hear what people are doing. I was the co-chair of the Summit on Drone Geophysics last year, which was a huge success. So I'm really looking forward to this year and the amazing lineup of speakers who we have presenting over the next 4 days. And Callum, would you like to introduce yourself?
Yes, thank you, Laura. Hello, everyone. My name is Callum Walter, and welcome to the 2022 Summit on Drone Geophysics. I will be one of the co-chairs for the first day, along with Laura. So I recently received my PhD from Queen's University, where I specialized in the design, integration, and optimization of drone aeromagnetic surveying for mineral exploration. Presently, I've taken up a postdoc research fellowship with the United States Geologic Survey, National Innovation Center, and the NASA Ames Research Center for Planetary Science. Here I'll be applying what I've learned in drone geophysics to develop innovative geophysical surveying techniques for off-world in situ resource surveying in support of NASA's upcoming Artemis crewed missions. This will be the 3rd year that I've been involved in the Summit on Drone Geophysics, and I can promise you that we have an exciting lineup planned over the next 4 days for everyone.
Yeah, we're going to kick off the panel, but I'll first of all start with introduction for each of our panelists. So we have 4 panelists today. So 4 amazing individuals who have shown that they're working in the forefront of drone innovation. So we're very happy they're able to make time for us today and talk with us over the next hour or so. Although the Summit on Drone Geophysics is mainly focused on geophysics, we feel that opening the door to a broader discussion at the onset of the summit will benefit all those either working or doing research or interested in what's next or where we are headed in the future and what challenges we may be faced. So let me begin by introducing our 4 panelists. So we have Kimberly Penn. So Kim started the first woman-owned tech firm in the state of Texas in 1993. Having thrived during the dot-com boom and bust of the 90s, Webtropolis is one of the nation's leading technical auditing firms for federally funded organizations subject to the security rule. She also founded 2 corporations specializing in AI, risk mitigation, drone technology, and audio-video in addition to IoT technology. Excuse me. Kimberly is a chief strategist for Women in Drones, a globally leading membership organization dedicated to driving excellence in unmanned aircraft systems, urban air mobility, and advanced air mobility, vertical takeoff and landing industries by achieving equity and participation of women in all disciplines and across all employment sectors. She teaches the current drone technology course related to aviation at Houston Community College. She recently designed the curriculum for a 5-course UAS certificate program, the UAS Technology Program, which launched in spring 2022. Kim has earned a double BA in Computer System Information Psychology from Houston Baptist University, an MA in Sociology from University of Houston, and an MPS in Technology Management from Georgetown University. And she's spent over 16 years teaching at the community college and university levels. So Lance R. Brady is another panelist today, and he manages the United States Geological Survey's National Uncrewed Systems Office, so NUSA, if I hopefully pronounced that acronym right, in Lakewood, Colorado. So NUSA was created in 2008 and has been on the cutting edge of small UAS research in support of the Department of Interior and USGS scientific missions. Lance spent nearly 20 years at the Bureau of Land Management in various geospatial and management positions. Lance worked in cooperation with the USGS NUSA office since its inception. Lance took the helm of NUSA in 2020, and he holds a bachelor's degree from the Northern Arizona University in Geography and Anthropology, studies at the Eastern Arizona College, and Aviation Technology at Cochise College. He is an FAA certified pilot and worked as an aircraft mechanic in his early years. We also have joining us today Roger O'Neill, and he is a pilot and a geologist currently living in Florida, USA. He's the owner and CEO of Overhead Intelligence, a drone mapping company which was founded in 2020. Roger graduated from the University of California, San Diego with a bachelor's degree in earth science and has spent 4 years in the field deploying advanced mineral exploration methods. Roger is also an avid pilot and holds an FAA commercial pilot certificate. He has built his own plane and has flown to over 30 different types, or has flown over 30 different types of aircrafts. His integral knowledge of the relationship between flying and mapping inspired him to pursue creating the idealized drone mapping platform, which we'll hear about today. So today, Overhead Intelligence works to collect wide area aerial data via UAVs with a focus on reducing collection costs for consumers of spatial data. And last but not least, we have Jamie Jacob. So he is the director of the Oklahoma State University Unmanned System Research Institute and the John Hendricks Chair and Professor of Aerospace Engineering in the School of Mechanical and Aerospace Engineering at Oklahoma State University. His current efforts are focused on advanced air mobility and their enhanced operations in the national airspace for broader innovation applications. He is currently led on the NASA University Leadership Initiative Program WindMap to develop aviation weather solutions for advanced aerial mobility applications, including drones and urban air taxis, and is the director of the Counter UAS Center of Excellence. As part of recent EDA fundings, he is leading the development of the Center for Advanced Air Mobility in Tulsa. He received his BS in aerospace engineering from the University of Oklahoma in 1990 and his master's and PhD in mechanical engineering from the University of California at Berkeley in 92 and 95, respectively. He is a native Oklahoman and dedicates much of his efforts to STEM workforce development, tribal engagement, and increasing diversity in engineering and science. So, big welcome to everyone here on the panel. Yeah, so we're going to have the Q&A box as well active, so please feel free to participate. I'm going to structure the panel so that I ask some panelist questions to get the conversation going and just to hear what we all think are some interesting and innovative topics that are at the forefront of drones. So I'm going to start by asking Kim a question. So the first question, Kim, is the increasingly popular use of AI in drone operations is replacing human decision-making and increasing public safety. Can you discuss public perception regarding the increased use of both AI and drones in research-based use cases?
Good morning, and absolutely, or good day, I should say, depending on where you are globally. Absolutely. When we look at drones, either separately and AI separately, one of the first words that comes to mind would be caution. The public perception of those two types of technology, one being software-based, the other hardware, is a great deal of caution in terms of how will this technology be used. And so I'm going to dig in a little bit and talk about what that looks like and how that's significant as you all as geophysicists and supporting go about interacting with the public on either public land, private land, and so forth with those. And so in terms of artificial intelligence, I think Hollywood has really impacted the way that the public looks at AI, that it has the ability to turn into Skynet or something related to, again, movies and things that can really be challenging for the public to have a great understanding. We know that the use of AI, which is the human decision-making, it's replacing especially some of the low-lying parts of how we make decisions, which can impact public safety. The integration between AI and drones using sensors and the ability to analyze and collect data will allow us to move more efficiently and more safely, particularly if we're interacting with the public or in areas where there may be people working or living, particularly where some abandoned wells may be. And so when I tie this all in together, it's important to understand how to address the public as you interact with them and how to make sure that there's a level of awareness. And so AI integration and the use of drones, it has some really solid data that's coming about. And as you're doing your marketing campaigns or anything related to, again, the research that you have going, looking at information to make sure you distribute. For example, 46% of the public is very weary of drones. And so if you're needing to go onto someone's land or, again, border something, it's important to understand that. I'm in Houston, Texas, and Texas is not the friendliest as it relates to drone usage, although it's a wonderful state for flying drones. And of course, Houston being the oil gas capital, we also have a number of oil and gas companies spread throughout the state. Now, we also have a lot of interaction with drone pilots flying out and folks having a very negative interaction with the pilots. And so we may have people that are threatened, for example, and we have people that will shoot at drones. And so how does that build into the public perception? It's, again, helping educate the public that the work that you're doing can lead to some great finds, also work on those abandoned mines and things, for example, but also what does that mean to the public and that you're not spying on their property or taking in information that could put someone in a vulnerable position. When I think about public safety, I also think about how we integrate AI into the actual drone, the piece of hardware, and we can take out some of the pilot errors that are associated with flight And so use of sensors, the use of the AI data and programming to allow for drones to better fly. Again, taking out some of the human error allows us to make some predetermined decisions and move over into associated action accordingly so that you can fly and go into even some of the line of sight opportunities that drones and AI can offer. And so we move from AI integrated into drones over into an automation aspect, and that in itself reduces the human intervention in some of our processes. And then it also leads to some sub-process relationships and actions. And so public perception, just to full circle, is pretty high related to cautious use of drones and AI, because those two technologies separately bring about quite a bit of anxiety for the public. And the more that we can educate with the work that we're doing and being good stewards of the interactions that we have when we're on public land or interacting with anyone in private sector, can really allow for a better feel for the public related to drones and AI.
Excellent. Yeah, I totally agree. I guess it's kind of two separate issues, AI and drones. So there's two technology you have to get into the public and help people understand how they can benefit us, especially when you're doing, I guess, construction projects, or you can take humans out of the situation and fly drones to do inspections. So really, they're a good thing. And yeah, I've encountered people who do think they can be used to spy on you or to take pictures. But yeah, that's just, they have other uses that are more valuable than that. So hopefully education will help people with that aspect.
Absolutely.
So yeah, the second question is, how would you describe the now and the future of AI and UAS?
I believe that the now is the use of AI, which is moving more and more towards the autonomous flight, which is very significant. It'll help, particularly if I look at the United States, our ability to move past line of sight, which is required for those who may be FAA Part 107. And so in order to cover some of these large masses of land, be it acres upon acres, the ability to integrate AI into the safety parts will allow us to continue to expand upon the use of drones. And so that's already taking place. We're seeing that in agriculture. We're seeing that in some of the policing aspects in terms of use cases for AI and drones. And we're also seeing that more and more as relates to the inspections, which is certainly a significant piece for geophysicists, for example. When you add LiDAR and some of the other technology that can allow us to survey and map out land, that's where we are now. As we add 5G and allow drones to be able to fly for an extended period, and again, move more and more into without needing to have line of sight. The future of drones will be the ability to, set up your initial map, get everything planned out, and you can continue to do some other work while that drone flies very successfully and certainly safely, autonomously over extended periods or and extended distances as well. Keeping in mind that the software that's available is ever changing and looking to integrate more and more AI. I think the necessity for programmers and those who really have a good understanding of AI, working with the hardware and the payloads is really where we're moving over to. And I think at some point, drones again will be able to turn themselves on with the right programming, take off, cover and capture, survey, and return so that the data, which could be cloud-based, is readily available to geophysicists and geologists and everyone else who may need to look at what's been captured. So I think we have some pretty exciting pieces ahead. It'll also give us an opportunity in the future using AI and drones to fly in more suburban areas and even heading into more urban areas safely. Again, taking out some of the human factors in allowing the aircraft along with the software to make some of those decisions in the interest of public safety will be a really exciting opportunity for the future of drones and AI.
Yeah, also, I guess the onboard real-time, processing allows for more effective data management, which I find really cool as geophysicists. Like flight paths can be adapted to areas of interest that might be identified during the flight, which is very, very cool. I just have a question. So training data sets are needed for AI work. Is there going to be a diverse enough amount of training data sets, do you think, or is that going to be a challenge to capture all the potential situations that could be encountered?
Right now, it's a challenge, and that's where I think some of our colleges and universities can come into play to help build out some of the data sets that allow for more of the training parts. And so looking for collaborations between, again, colleges and universities who often have the technology and the tech stack. I know that NVIDIA, for example, just recently donated a 400K computer that will allow for AI data sets to be captured to Houston Community College, which is a really significant donation for that type of technology, which of course can be used in the UAS space in all aspects of AI and moving over into automation. And as always the case, I think startups will start to really launch that will focus in on some of those training data sets and making them accessible and available to organizations to do some of their prelim and use case testing. And so there's always some opportunity there, but we have lots of room to grow. Data sets can be expensive to build as well as to store, even cloud-based. And that's really what we'll need so that people can have access and pilots can have access, for example, to those data sets globally. There's lots of room to grow, and we look forward to seeing what that looks like moving forward.
Excellent. Yeah, definitely something that's going to be future important in our future.
Very much.
Just seeing. Thanks so much, Kim, and feel free to chime in at any other time. I'm sure potentially conversations will circle back. But Lance, I'm going to ask Lance a few questions from the U.S. Geological Survey. So how will the Presidential Executive Order and the Defense and Innovation Unit Blue Drone program affect or potentially affect federal contracting opportunities and research grants? There's also pending legislation that may limit federal funding for covered UAS, which is definitely going to be an issue for, I'm sure, a lot of people.
Thank you, Laura, and it's great to be here today, and I appreciate the opportunity to speak with you. You know, the regulatory space we're in the United States is at times challenging, but it also has some great opportunities that we've been able to participate in the national airspace for some time. And we've done so, for the most part, pretty safe operations. Now, the Defense Innovation Unit is part of a DoD program where they have vetted certain aircraft to meet certain cyber vulnerability testing. And through that testing, they've pretty much come up with cleared aircraft that are specific uses for the federal government, the United States federal government. And many agencies are under restrictions to purchase drones from companies that are produced or using parts that are from friendly countries. And so it is really put limitations on the types of aircraft that we can operate within the Department of Interior. As we move forward, there is an executive order, presidential executive order that came in under the prior administration, but was upheld by the current administration, which limits federal funds on the use of what they call covered UAS. And so it really limits for universities and researchers that are interested in using federal funds for their drone operations, that they'll have to look at those aircraft, not specifically the Defense Innovation Unit blue cleared drones, but they will have to go through some kind of vetting process to make sure that the cyber vulnerability and the federal funds that are migrated over to the manufacturing companies are used for friendly countries. And so just to be aware of those limitations in the future, there's also pending legislation we have to keep our track on, which could also limit not only federal funds, but the type of operations the federal government and partners can operate. And we have seen where things that are going on with the federal government have also been adopted by several states within the United States. And so you're seeing that it's quite the talking points right now when it comes to some of the countries that we're currently operating drones in the United States. Don't know how much that will cross into the private sector, but if there's any federal funds, you just need to be very cautious of the aircraft you're flying and how you're funding those type of operations.
Yeah, for sure. And like you said, you're not sure how that affects the private sector, but it's definitely an issue if you're doing government work. Yeah, so the next question, I guess, follow up on that, are what are the USGS or NUSA challenges in integrating VisNear, so visual near infrared hyperspectral line scanners on small UAS? And what have been the lessons learned, including radiometric calibrations for your team?
So pretty good question. I think, as we've gone over the years, we've taken baby steps in integration of sensors over the years, starting with, basic photogrammetry type missions going back into the early 2000s to advanced sensors. Kind of the latest and greatest is hyperspectral imaging. Some of these hyperspectral imagers are not designed for aerial applications. For the most part, these scanners are developed for laboratory use or within production lines, where it may be parked on a specific mount and it might be monitoring certain produce that's coming across a conveyor belt, and it's having to determine which of the vegetables or fruits are good to pass on to consumers and those that need to be rejected. And so it's a very fixed type system. And what we're trying to do is put that in an airborne solution where we have a lot of things that are moving at the same time. We have the aircraft moving, we have the ground moving, we have differences in the elevations that we're operating. And so there's just some very unique challenges about orientation of the instruments. And, with a traditional photogrammetry type payload where it's a fixed frame imaging sensor, these are push broom scanners. And so to make sure that we have pixels that are square and not elongated, it takes quite a bit of sensor and computer power to make sure that we're defining those pixels correctly and we're placing those pixels correctly on the Earth. And so there's a lot of challenges with that from the IMU perspective, and also with not fully understanding the complexities of low Earth type imaging of the hyperspectral. And so one of the challenges that we've experienced is, a lot of the manufacturers aren't quite accustomed to airborne applications. And so like for the case of one of the hyperspectral units we're operating now, over about a year and a half of testing, it's determined that we need to fly that instrument with a co-located LiDAR unit as well. So we're not only flying hyperspectral, which is a pretty expensive instrument, but we're also having to add on a LiDAR instrument on top of that as well, so we can get near real-time DEMs for rectification of the line scan. And so it's pretty challenging. In terms of the calibration of the instruments, there again, these are typically designed for laboratory use where the environmentals are pretty controlled. And when we get into the case of flying these on drones, it's challenging because you have incoming radiation that you're having to measure. You're having to take a digital number that's coming off of the instrument and actually get to a reflectance value that we can tie to other instruments or ground-based spectroscopy, or where we're looking for specific things. Now on the shortwave infrared, or the VisNear, the visible near infrared side, where we're mainly looking at vegetation, that's the kind of the space that we're in right now. But as we move into to larger aircraft that can carry a heavier payload. We're getting into the SWIR, the shortwave infrared type hyperspectral scanners, which are a lot more expensive. And those are more suited for the soil and geologic applications that we're hoping to move into doing some critical mineral analysis and determination. So it's a big challenge. I don't think we have a product yet that we're comfortable with giving to our scientists and determining that these instruments are accurately reflecting what we think the subject that we're looking at. We're just not quite there yet with our hyperspectral. We're hoping to be there within a couple years, but we're just having challenges at the moment. And hyperspectral is very different from multispectral and LiDAR and photogrammetry applications.
Are you mounting those hyperspectral sensors on the drone itself?
Yeah, for the most part, they're on a gimbal mount. We are probably going to be moving away from a gimbal mount to a fixed mount on the drones, just to ease some of the issues with the IMU and placing those, like I said, those pixels on the ground correctly and making sure that they're square. So those are the two types of mounts that we're using right now, both a gimbal and a fixed mount.
I remember I was at a conference a couple of years ago now, and they were talking about developing hyperspectral, and they said one of the things that was unique to that, as opposed to say some geophysical sensors, was there's a lot of vibration issues with mounting the sensors on the drones, and that seemed to be one of the challenges they had with it. I can't remember the specifics of it, but I don't know, maybe you have some idea of that.
Vibration can be an issue. We make sure that, a lot of our current platforms that we're operating are, props are balanced. We don't have as much of a vibration problem. I think, it can be an issue, especially with unmaintained aircraft. But generally the aircraft that we're operating are pretty stable and have limited vibration. I mean, it's always going to be a problem, but we try to dampen it as much as we can.
Yeah, with UAVs, you can use gimbals, which is nice. So with fixed wings, yeah, it's harder.
Yeah, and I should mention that at least right now, the hyperspectral scanners that we're operating are all on multi-rotor, multi-copter type platforms.
There's a question in the chat, I think that's relevant, which I guess there's state law and then there's federal law for drone acquisitions. What you're talking about is the Blue UAS program, which is a limited list of drones that people can acquire. And I think state law just basically refers back to the Blue UAS. Well, most of them refer back to Blue UAS and say, if the feds approved it, then we'll approve it internally. My question would be it takes a long time for a UAS to get on the Blue UAS list, but a company could get either a waiver or become NDAA compliant prior to being on that list. Do you know what the waiver process looks like, or if it has to be a Blue UAS, or if you can get an NDAA compliant drone if it doesn't meet the other ones don't meet your standards?
Yeah, so it's a pretty complex question that you're asking. I'm going to speak specifically about Department of Interior and what our policy says. So our policy says that as of right now, as of last Thursday, we have to purchase off of the blue cleared list from DIU. We had some changes on Friday where we're not as pigeonholed into the DIU blue program, but the aircraft still will have to meet both NDAA and future legislation. And I guess the elephant in the room is really the presidential executive order that speaks to the parts and components of the aircraft that cannot be either manufactured whole or in part in a unfriendly country. So the executive order is what at least our new directions moving towards. So some states have looked at the federal government and determined that they can only purchase out of the blue program. As of right now, it's really the only group that's out there vetting systems for cyber vulnerability, at least to certify them. And so that's why we've been down that path so far. I can't speak for the states and their decision-making process and why they determined that that's where they wanted to go with recommending only the blue drone program. But it is a challenge for manufacturers. And at least with the Department of Interior, I wouldn't say we're completely moving away from blue drones, but we will have to determine another methodology for making sure that the aircraft we're operating are manufactured in friendly countries. And that's all or in part, including some of the major components.
Hey, so I've been running into the same issue. I do a bunch of like contract work. And so there's projects that I'm working with the National Park Service and like Forest Service and other kind of folks. And like realistically, we've had to, it's been a pain. So we've had to actually shift from using kind of Chinese made things like the Theo 140, which is like a giant, essentially like gas electric hybrid quadcopter that can fly for like 4 to 6 hours. We've had to switch to like the Alta X. I mean, they won't let you fly them. Like it is what it is.
Yeah, and that's at the beginning when I mentioned about limitations on federal funds for procurement of UAS through contracts. That's one of the challenges is that, you know, if a vendor were to want to either work for the federal government or get federal funds for any type of research through a university, they just have to be have a little bit of knowledge in what limitations may come with the use of the federal funds. And Timothy was right on it. It has impacted some Department of Interior operations and the types of aircraft that can operate under contract.
Yeah, that kind of ties back. I'm just thinking now to public awareness of drones. That just puts that little bit of anxiety in people as to, okay, why did we even establish the Blue UAS program? And people just hearing about that might think, okay, well, this is an issue. But
it's a challenge, and it is a challenge, and you know, we have to do our part as within the UAS community to educate not only our lawmakers, but also the public on the types of missions that we conduct. There's no real difference in the instruments and the aircraft that we're operating compared to crewed and manned aircraft as well. So it's a challenge. Most people, if they see a crewed helicopter, a fixed wing aircraft flying overhead, they don't immediately think the worst of the situation that somebody's observing.
Right.
You know, our private stuff, even though some of our imaging cameras are more capable than what we can fly on the uncrewed side.
Right. Yeah. And just to add to that comment or question that Roger read out. So yeah, this person said in Florida State University, we can only purchase drones that are very specific shortlists, so none are useful for their research, unfortunately. There's another question that came in. How have drone geophysics or AI been applied towards civilian or / government use, such as search and rescue? Have people been able to leverage capabilities beyond visual data, combining thermal, infrared, or even acoustic sensors successfully? So that's a question, yeah, surrounding civilian and governments using for search and rescue, which I think it's being used quite a bit.
Laura, is that a question for me or the panel?
It's a question for the panel. If anyone does have experience in it, maybe they could take it, and if not, we can leave it for the discussion.
I'm happy to chime in a little bit on that.
Okay.
Here in Houston, we're building a resiliency center, which will be a training center for first responders. FEMA is part of it, Department of Homeland Security, and then some of our city and county agencies, and drones will play a significant part of that, because we can use those and very much so in a search and rescue. And so some of the examples could be Houston, for example, has a lot of severe flooding on a good day. You have a little bit of rain and it turns into a whole water event. In that case, if someone is, say there's a car or a bus full of students, just not to sound too dramatic, but has been impacted by the flood and have now left the vehicle in some form or fashion, search and rescue can head out. A drone operator can also go out on the scene, and using some of the heat sensing in terms of sensors, help the search and rescue team, even before they step foot in any water, determine where people are immediately. We can also add the ability to communicate with those individuals with the use of the drone, so that we can assure them that we are aware that they're in a particular location and that help is on the way. And so I think we'll see that more and more across the United States, and I think even globally, the use of UAS, artificial intelligence, that allows for flight in very challenging areas, and so that the sensors and hardware can really work together and navigate, whether it's dark, trees and other things that would make it pretty challenging for a drone operator to really fly. Again, the AI can make some of those human decisions and take into account the public safety. And so that's becoming more and more funding is becoming available for that as well.
Yeah,
Excellent.
Laura, in terms of USGS operations and also Department of Interior, we have a large component of our operations that are in emergency response, specifically in the wild and fire mission set, where we do a lot of both beyond visual line of sight operations, nighttime operations to mitigate issues with the manned aircraft operations during tactical fire missions. We also, specific to USGS, during the 2018 Kilauea eruption in Hawaii, our crews were there 24 hours a day for about 7 months during the eruption. As part of that mission set was also search and rescue, as some of the lava flows were coming into some of the communities. And so we were using the aircraft to actually locate individuals and then being able to communicate with them through cell phone and emergency response in the emergency operations centers to mitigate where they were at and walk them from the scene where they weren't going to be injured through basically the lava flow. And that most of that was being conducted at night, where it was pretty difficult to get situational awareness. So we do have some experience there. I think as Kimberly mentioned, with AI being able to reduce the pilot workload and reduce the workload of the staff around, I think is pretty critical in moving forward with, especially in search and rescue. Search and rescue is challenging with drones just because it's like looking through a soda straw and you don't really get the full perspective of the environment around you. So that is a challenge, but using advanced sensors is pretty helpful. I'm not sure what the tie-in is to the multispectral. We do conduct a lot of different missions, not specifically looking at search and rescue with our multispectral imaging or even hyperspectral LiDAR, but we do try to bring the most latest technology to the game.
That's a really exciting application there, just to help people stuck by some lava flow and then have this safety drone come by. It's just amazing. And then Timothy pointed out, not for search and rescue, but for UXOs. So I guess we'll talk a bit more about that as well, how those different sensors are used to detect UXOs.
So, do you want me to say something or no? Because the
yeah,
UXO
sure.
stuff it's so visible light stuff. What we've been working on in terms of the convolutional neural network algorithm, we have a faster regional CNN that we've been working on, and the accuracy is up to about 93% now for visible light imagery. But as we all know, the days are growing cooler. I've got outside my office, all the leaves are falling off the maple trees, all that stuff. Those sensors are only going to be able to work during the hours when we have daylight, right? What we need are sensors that can work pretty much 24/7. And so when we're starting to think about that, it's obvious that we have to start adding thermal sensors and magnetic sensors and all types of things. The problem with some of these sensors, though, is like Ron and a lot of folks who've kind of played around with a lot of the hardware know, is that the ones that are just imaging the surface, those can be 24/7 in terms of UAV acquisition and still have a high ground sampling distance. But the sensors that are mostly geophysical sensors, whether they're passive, like magnetic sensors, or whether they're active, like ground penetrating radar or time domain electromagnetic induction, those sensors are necessarily going to be limited by the fact that you actually start to have a fall off of the anomalous field that you're looking for as you rise. So magnetic sensor is going to fall off at 1/r², where r is distance, right? And then for an electromagnetic sensor, it's going to be even worse. It's going to be like 1/r, like r to the sixth. So like it's just we need to kind of like think about outside the box so that we can be demining pretty much 24/7, especially in places like Ukraine. I don't know how much y'all know about the conflict in Ukraine, but I've been there. I've done demining research there post, the 2014, 2015 kind of conflicts. And I'm going to be going back once this one's over, but there are TM62 anti-tank mines just everywhere. I mean, they're in urban areas, they're in rural areas, they're in areas where there's, tractors for farming. As we know, more or less the effect of this war is going to be that potentially tens of millions of people are in famine situation. And it's not going to be in the first world. It's going to be in the third world. So demining this area fast using efficient methods like UAV-based remote sensing methods is going to be huge. So that's kind of in terms of where we're moving. And these data that we're creating are also enormous. Like I'm going to be talking with you all about hyperspectral imaging here in a talk here in about an hour, I guess. And I collect data for 15 minutes as 150 gigabytes of data. And with thermal, it's not very different when you're using 30 hertz cameras on multiple drones. So we need to, we're way past the, the computational kind of, oh, it's hard to visualize this. Like that's easy. Now we need to start handling large data and actually managing it so that it's not human eyeballs looking for things. It's, machine learning algorithms. So.
Excellent. Yeah, that's a great take on a lot of the issues there. I think in the interest of time, we'll move on to our next panelist and get our questions going with Roger. So Roger, what are the major challenges of using drones for large area geophysical mapping operations?
Okay, so a lot of people are talking about really interesting use cases for drones, but we're mostly focused on the actual platform side, which is not really the sensor, but let's just say you had a sensor that you attached to a drone. Let's say you wanted to cover, 100 square kilometers of area. A lot of people would look at that and say, no, thank you. We'll just go get a helicopter or whatever, and that'll actually cover the region. So there are reasons why people are turning away from drones for some of these large area collects is because they're logistically complex. And there's a wide array of challenges that prevent people from doing anything at scale with a drone. In my opinion, there are basically three primary challenges with doing large scale, the biggest one being regulatory. So if you don't have approval to go beyond visual line of sight, then you can't legally operate it. Now, that doesn't stop people. There are probably people in this call who have experienced beyond visual line of sight flying sans regulatory approval, particularly in low risk areas. So I know that it happens. It's just sort of the nature of what it is, but to have the graces of the government at the same time to operate would be ideal for everybody. And there is actually huge risk with flying beyond visual line of sight anywhere. If you're out in the middle of nowhere doing exploration geology, I get it. But if you're in, somewhere in Texas, like Kim was talking about, you got to deal with, not only are people probably not happy with that drone being there in the first place, but then they can now have some regulatory restriction on that operation. So there has to be reconciliation with the regulations. To reconcile the regulations, it's really a technical problem. And that's what I want to talk about is, if you want to go beyond visual line of sight, you need to make sure you have good radio connection. And then you actually have a drone that can fly that far. And then once you get out that far, talking about the AI, I don't really call it AI, I more call it machine vision. The drone has to actually know what's going on around it, because if you can't see it, then it has to know what's around it. So there's the three technical problems beyond regulatory. In order to solve the regulatory problem, you need to have good radio connection, good range, and then machine vision. Now, Kim talked about 5G, but where you're mostly doing geophysics are places where there's no cellular connection. So having a good radio that gets you a long distance is critical to actually doing a large scale collection. And there is not a single off-the-shelf drone solution that has that today. And I've experienced that as a part acquirer, that you can't just go and buy, a free fly out to X and expect it to get you out to 4 kilometers or more. And on top of that, if you're typically doing geophysics exploration, you're in terrain, and RF is line of sight. So getting an RF signal over a hill is impossible unless you have some other methodology. And that's one of the things that we focused on heavily at our first launch was, how do I get consistently, legally we can go 4.5 kilometers from launch, or sorry, 3.5 kilometers from launch. But technically, if you have a hillside there, I can only go as far as the RF will propagate. So how do you mitigate that risk and get further radio connection, particularly when you don't have things like 5G or very expensive sat links and things like that? And then if you can get the radio link and you get out there, then you now have the problem of, okay, can I keep the drone in the air long enough for it to even be justifiable? So, taking most of your off-the-shelf drone components, they're battery powered. And I mean, Lance can talk about this, about how, taking an M600 drone, which has 6 battery sets on it, and trying to run it for an entire day when your flight time is 6 minutes, especially at high altitude. So how do you get, when I say range, I really talk about, the endurance of the platform. A lot of people can say, oh, our drone flies for 60 miles. Great. But now you have to combine that with a radio and then get it out there, and combine all these technologies together. You can't just have one solution. It needs multiple pieces. So the issue that with radios is probably one of the key elements, and that also restricts your range, which is an endurance question. So the one step down the line is, okay, you're flying beyond visual line of sight, which is basically large scale implies beyond visual line of sight. You have to go beyond visual line of sight. So let's say you have a regulatory approval and you you have your radios, you have the long endurance drone. You now have to, especially for MAG, one of the things that Tim just mentioned is, factor of 1 over r squared or r cubed fall off with height. So the closer you can get to the ground, you get exponentially better results in resolution. And I mean, I'm a pilot, Lance is a pilot. Flying low is not fun. It's also not legal for fixed wing perspective. In helicopters, you can do it. But when you get down and, with the birds and the bees, it's kind of scary. And this is where I talk about machine vision, which people use the word AI. I don't really understand what that means practically speaking, but I understand, like, if you have a feed of data coming in, the drone needs to see that feed of data and determine what is something that is noise versus what is something that I need to avoid. And one of the things that we focus on, again, is IFR capable and nighttime capable machine vision systems. And Tim said, okay, great. Yeah, your optical scanner only works during the day. Well, what happens if it's raining? Or what happens if it's bad weather? Or what happens if it's dark? So this is why we focus specifically on radar, so that you can detect the ground surface and fly as low as humanly possible. Because UXO is a complete non-starter unless you get close to the ground. And you're basically flying at top of canopy. And unless, what a lot of people do to solve the problem is, okay, great, I'll go and collect a photogrammetry data set a couple days before, process it, have a high resolution digital train model, and then I can follow that. Now you've added, a couple days and a bunch of labor hours to the project when somebody would just, switch over and use a fixed wing aircraft. So I guess in sum, the big challenge to do large scale geophysical operations is you're competing with a very old established industry of manned aircraft that's very good at what it does at large scale. And if you can't match their scale and production in a reasonable timeline, then it's people won't want to use that product. We've obviously faced that challenge pretty immensely. And the 3 things that are really we're heavily focusing on to solve that are long range radios, long endurance drones, and then a machine vision for anti-collision systems so we can fly low, mitigate those risks. And combining all those things, we've been able to do monstrously large scale beyond your line of sight waivers, particularly in Canada, to actually operate drones safely and legally at these long distance metrics.
Excellent. Yeah, I know in Canada, one of the things that I'm really kind of looking forward to on the regulatory side is that, we have a lot of these open spaces away from people where we can be testing a lot of these different systems moving forward. So, these long range capabilities and getting this out of kind of, the urban centers in the US, where if you want to fly like a really large area, you're probably going to be flying over people. So Canada, I mean, I hope this comes along, within the next 5 years or so, where Transport Canada allows us to be able to test some of these technologies and use them in these remote places to kind of prove that these are viable so that we can then go and use them in a lot of these more riskier places. There are some questions I know too, like just with the size of the drones, because I think Natural Resource Canada is looking at flying basically, a mini airplane that's decked out as a drone and trying to see if that's going to work for running their MAG surveys moving forward. But then maybe operators like you are going to be looking at, just a wingspan of 2 to 4 meters sort of thing for a drone. So there's also a different space here that we have to see how this is going to compete with the regular manned systems and, of course, data quality and everything. So it'll be interesting to see where this goes in the future.
You talk about, so one of the reasons why we operate mostly in Canada, I mean, I'm an American, but we operate mostly in Canada because there's a specific policy that Transport Canada has that the United States doesn't, due to population density. And Transport Canada has effectively broken the country out into 2 ground risk zones. that segregates between a sort of high ground risk and a low ground risk zones based on population density. And from a waiver application process, if you can identify what zone you're in and use that as some of your risk mitigation, they're actually much more open to you doing more experimental work. So this has also been identified by, it's not Intel, General Electric. So General Electric is doing their R&D work in Canada for this reason, because you can operate at large scale by mitigating your ground risk. And then, the caveat to that is if you wanted to scale it into more urban areas, you now have to solve the ground risk issue prior to actually solving that problem.
Yeah, and I think once we start to be able to solve that and prove that it's less and less risky to fly these kind of beyond visual line of sight surveys, it's it'll just be able to move forward from there. So really looking forward to that. Does anyone else have anything to add to this before we move to the next question?
Question did come in the chat or in the Q&A box. So what do we consider long-range drone applications? You can quickly, you get quickly to scale with where aircraft is cheaper, and then especially light, less than 500 kilogram aircrafts. So the question is, what are considered long-range drones?
I love answering this question, and this goes back to something that Tim said. A manned aircraft, and going back to those of us who actually fly airplanes, if you're collecting mag, you have to fly low. And I'm mostly focused on mag and LiDAR. LiDAR is a different animal, which I won't talk about, but if you're collecting mag, you have to fly low. And if you're operating in a manned aircraft, the only time you're realistically going to operate a manned aircraft is during daylight, day VFR hours, because you're relying on visual aids to not hit stuff. And north of 60 degrees, which is a big portion of Canadians, or really the world's exploration districts, north of 60 degrees has no high resolution train data sets. So if you wanted to rely on SRTM data, you can't. You just have to basically look outside and not hit things. So long range, I don't think about it in terms of linear distance from I'm covering, I'm traveling 150 miles. That would be the case for like a corridor or utility inspection. The long range is more about a total area covered in a single flight. And there's a gap right now. If you're trying to use an M600, it's practically impossible to crank out more than around 100 line kilometers a day. And I'll caveat that by saying that as long as you're not going more than 2 kilometers from your launch point, then you can effectively crank out as much in that small area at very high density with an M600, but it's logistically quite challenging. What we look at is, right now we can do over 280 line kilometers a day, and our maximum coverage area is we can cover about an 8 square kilometer tile from a single launch point. So that's sort of our metric. But the beauty is, in the long run, Tim talks about running 24 hours a day. A drone doesn't care if it's light outside, as long as your sensors aren't dependent on the visible spectra to operate. So GPS doesn't care about daylight or weather, and neither does radar. And the Transport Canada does. They care about those limitations, but there's a matter of time when you can actually do sort of an IFR certification. And then going back to sort of the automation of the system, you can run some simultaneous systems at the same time. And now, yes, you're right in saying that you can very quickly get to a size where an aircraft can beat you. But right now, I can outproduce a fixed wing mag survey if they're doing 30 by 50 meter surveys. In pricing, we can beat them now, and I can match their coverage as long as I'm within my waiver restricted zones, which are in Canada. It's just a matter of getting regulatory approval to go beyond that if you want to do something bigger. So the pricing now already beats the aircraft scale, but traditionally, you would be correct by saying that once you get beyond it's probably like 60 square kilometers, then an aircraft is effectively your best bet. Like if you're going to do a 50,000 line kilometer survey, it would be very challenging for somebody to outbid you with a drone at the moment. But anything less than 40 square kilometers is absolute fair game. And that's where a lot of claim structures are for the exploration space. They're in that sort of size and scope range.
Well, if no one else has anything to jump in with that.
There is one, Callum.
There is?
Yeah, there's just another question.
Perfect.
Yeah, so in urban areas, could Amazon be approached to share some of their UAS experience / data flying? Sorry, I just jumped. In different FAA higher risk airspace zones. So in urban areas, could Amazon be approached to share some of the UAS experience in different FAA high risk airspace zones? Does anyone have any experience with that? So
Amazon-
I guess assuming Amazon's using.
Amazon just
More
canned
space?
their UAS program, so I don't know what they're up to, but they're
Okay.
dialing back a lot of their operations on the delivery side. I don't know if that helps.
Okay.
I'll just jump in and say, for those that are doing urban ops, such as Google, the Google Wing program, they are really limited in terms of the spaces that they're operating in. And I would call them mostly suburban rather than urban locations for some of their delivery tests that they're currently doing right now.
Yeah, good to know. Another question, what are they flying in Finland different to get large beyond visual line of sight mag surveys, say compared to Canada or US? I saw that I wasn't aware, but something, what are they doing in Finland that's different? Does anyone know anything about that?
I know for a fact that there are much larger weight classifications that are waived in those parts of the world. EASA has given approvals to a number of very heavy lift hybrid helicopters in particular for mag surveys, which I've seen. But the United States and Canada don't like things over 55 pounds. And you have to, in the US, it's used to be called Section 333 exemption if you wanted to go over that. I think 46802 or whatever the new regulatory code is. But if you go over 55 pounds, if you think getting a beyond visual line of sight waiver is a lot of work, then getting a over 55 pound waiver and a beyond visual line of sight waiver is exponentially more difficult. So paperwork gets above 55 pound paperwork is practically impossible. And I don't know what the case is in Finland, but I do know for a fact in Europe, they are running, and even in Africa and India, they are running larger weight systems. That solves a lot of your problems to start with.
Yeah, the current EU regulations are a lot more flexible than what are offered in the US right now. And I would imagine, I'm not familiar with, Finland's case, but since they have extremely low population densities there, it makes the safety case, very easy to justify.
Well, I think now we'll move on to the second question for Roger, which is what are some of the key things to know when applying for BVLOS or beyond visual line of sight waivers?
Beyond visual line of sight waivers are really, it's a procedural exercise, and anybody can do it. If people are thinking about going beyond visual line of sight, don't be intimidated by the fact that it's a lot of writing, but if you read and write English, then you can get yourself a beyond visual line of sight waiver. I'd say that the most important topics to consider is back to my three main points is, can your hardware handle beyond visual line of sight? And if your hardware can't handle beyond visual line of sight, there's no point in getting a waiver. If you can't maintain your radio connection sustainably, the FAA is going to require you to maintain link. And I know this is a standard practice in the industry to actually send a drone out, lose link, and wait for it to come back. And you basically turn the automatic return to launch function off. That's not legal on the FAA's eyes, and you can try and get away with it for a long period of time. But if you don't have a stable radio link on your drones, then that you're no longer operating under your waiver. So there's almost no scenario where you will be able to get a waiver and not have a stable radio link. So I guess the theme is that your hardware must meet the regulatory standards. And those are basically the three main topics that I spoke about. Is you need to be able to have the endurance, you can have the link capacity, and ensure your collision avoidance is there. And then the two things that you're trying to focus on for the collision avoidance is effectively colliding with terrain and colliding with other aircraft. And so those are your ground and air risk mitigations. And if you can mitigate, that's actually a hardware mitigation. There are other sort of procedural mitigations you can do for the ground risk, which Canada specifically has pathways for. And also in the United States, you can statistically mitigate your ground risk. But that's just it's a verbal case that you must make to the FAA or Transport Canada to get those waivers approved. But in general, should you have your hardware meet the standards, you also then can mitigate your risks. Then it's just a matter of compiling that into a concise sort of set of procedural documents and implementing that as a practice into your organization. And then you can actually go out and operate safely and legally on a beyond visual line of sight waiver.
I know one thing with Transport Canada specifically, when they started moving towards waivers as part of their operational procedure to allow people to fly, was that once you kind of establish yourself with them and apply for a waiver, show that you can fly compliantly and safely, and continue to move that forward, it becomes a lot easier for them to be like, yep, okay, they're doing another survey of this caliber sort of thing, and then approve you. So once you get the process started and the ball moving forward with that, it becomes a lot easier for them to approve this sort of waiver once they have a relationship with the company.
Yeah, that's a term that we call operational credit. If you have, prior beyond visual line of sight experience is almost a prerequisite for future beyond visual line of sight approvals. And so if you can go in a sort of low risk in that scenario and demonstrate your safety case on sort of the baby step approach, it's much easier to get past that in the long run. If you're trying to do, you don't go to the FAA or Transport Canada and say, hi, I'd like to survey all of Newfoundland. They just, not going to happen. But I will say, like, as Callum said, your turnaround time gets much shorter every waiver you submit because they already are familiar with your core body of documentation. You're really just submitting a minor amendment. And if they've approved the core body and you can demonstrate that you've adhered to that restriction, then getting a small amendment is a 20-minute task for them. So they just read the amendment and then you can have very short turnaround times to get more waivers.
Does anyone else have anything to add to BVLOS waivers or kind of that process with trying to fly beyond visual line of sight from a regulatory perspective?
Jeff just added a comment, I think, regarding the Finland operations. He said, I think they're using petrol fixed wing drones for one reason, I guess. That's okay. Just to add to that, petrol fixed wing drones might be easier to get to regulations in Finland.
I will say one thing, if you're not gas powered, it's not going to work on large scale because battery technology is not there. The operational logistic requirements are just, they make it practically impossible. So if you aren't, and Tim mentioned that he had the, I guess it was the, I can't remember the name of the drone, the Chinese quad that used the Foxtech engine. There is a company on the Blue UAS list that has that same engine. It's Harris Aerial. They're based here in Florida. So if you are a government entity looking to acquire a long endurance drone, they exist. They're approved. You can get them. They work. We have 2 of them. They
do work. Yeah. Like they're not that bad. I mean, you just have to calibrate them. And I don't know what mission planning software you use, but they're pretty awesome. So, and you can get all types of, so you can get them to be Pixhawk or you can get the A3 if you're more used to DJI products. Like they're sweet.
Thank you, Roger, very much. I think we'll move on now to Jamie Jacob, and I'll have a couple questions to ask. So the first question is, how will changing regulations open up or further restrict the use of drones for geophysics?
It's a pretty broad ended question, but I think a lot of the comments have already addressed that. We're currently in a pretty rapidly changing regulatory environment right now. But the FAA is still, hesitant to open up most of the U.S. national airspace to beyond visual line of sight operations. So, that is kind of very slowly being rolled out in, a number of limited cases. What they've really been pushing is, the use of Part 107 waivers. And so for most of the public agencies, which in the past have used COAs, to be able to get those, our beyond visual line of sight operations, for example, in higher altitude flights are, mostly using COAs rather than Part 107. The FAA has been trying to transition a lot of those waivers and requests, back to Part 107. They're still very hesitant to be able to move on to beyond visual line of sight, but as remote ID is, more widely implemented, and we'll expect to see that change as well. However, timing is going to be a big question on that.
Yeah, one thing I wonder with the regulations is, do you think it'll ever move towards a point where, like, say professionals that are working in the drone space, so running geophysics or running, precision ag or something like that, would there be separate regulations for people like that as opposed to just the general public? So I think of just like, the general YouTuber who has a drone in their backpack, throws it up to capture, a train or something, where maybe there's some legal questions regarding that, where it'd be different for us.
Yeah, there have been discussions about that, particularly from the FAA rulemaking committees, and they're just implementing another one, which is going to tackle some of these questions, particularly related to BVLOS operations. I don't foresee that just from the standpoint of the FAA, really trying to keep the airspace open, and they're treating all UAS and drone operators as one large group, regardless of how useful I think that would be, to be able to categorize operators, under you could almost think of this as like a Part 91 versus Part 135 type of operation, where you could, set aside a Part 107/91 set of rules. And they still encourage, using experimental airworthiness certificates to be able to do a lot of that. But again, that's pretty onerous on kind of the average operator.
Yeah, I was just wondering if there's kind of a trend with that, because when I remember first flying, back in 2016 in Canada for like the experimental payloads of slinging a mag underneath it, and it was like 10 times more onerous for a researcher like myself to be able to go through kind of the waivers, as opposed to just, someone who has no flight training or flight experience to just go and pick up a drone off the shelf and fly almost in the same places. But yeah, I mean, it does make a lot of sense, because it's hard to control everyone who's flying and what they're doing, for sure. Does anyone else have any other thoughts on the regulatory side? If not, then, and I don't think we have any questions in the chat at the moment for this one specifically, I'll move on to the next question for Jamie, which is, what non-conventional platforms can be used for surveys, and what novel sensors are on the horizon?
Well, one thing that we've been doing that's particularly interesting, and this has been driven by NASA's interest in extraterrestrial seismology, particularly for planets such as Mars and Venus, which have, similar geophysics, but to that of Earth, or similar, at least, that we can use a lot of the same tools that we currently utilize here on Earth. But there's still so much unknown about particularly the early origins that they had on both of those planets. So one of the things that we've been utilizing are high altitude weather balloons, both helium and hydrogen lifts, so lighter than air systems, and also kind of unconventional solar balloons, which use solar heating. And these systems allow altitudes way above what you get from normal platforms, anywhere from 60,000 feet and up, and very long flight times. So currently we're evaluating the use of infrasonic sensors deployed from these balloons to be able to do large detection volumes for seismic events, detecting earthquakes, in the order of magnitudes 2 and up, using those systems. So while primarily this is being driven by interest in seismology on other planets, we're also finding value using that here. And those seismic sensors are primarily looking for infrasonic signals, below the threshold of human hearing, and had previously been developed for monitoring for nuclear explosions, nuclear tests, as part of the Nuclear Test Ban Treaty, but have also been used for detection of meteor impacts with the upper atmosphere.
Very fascinating. So from the seismic perspective, for putting the sensors on the drones, you're actually measuring kind of the seismic waves as they come in the atmosphere to the drone, as opposed to, I know there are some people that work on, drones that kind of either try and collect data from seismic stations that are on the ground, either through telelink, but this is actually the sensor on the drone being able to.
Yeah, and a lot of this was originally born from, some of the work that we've done with drones essentially communicating with ground-based seismic sensors in order to pick up that data. So, which has traditionally been hard to get back to the network. But in this case, the sensors themselves are on the platforms. And we've done some very limited UAV flights with these, but due to the interference that you get from either fixed wing or rotary wing drones, due to the acoustic signatures, those are still kind of early in the development. But the primary issue with that has been, since it's so hard to determine where a seismic signal is going to be at, you need a fairly large altitude to have a large field of view to be able to, see the ground over a large area of, radius of 100 miles or more, to be able to pick up those seismic signals.
Fascinating.
There's already been limited, we've had some limited tests both in Oklahoma, Texas, and California to pick up those earthquake signals. One of the things that we're doing right now, we typically have multiple sensors that are on a single balloon separated by about 100 feet of line, primarily due to the sampling rate and the ability to differentiate the altitude detection times, and that gives you essentially an ability to determine bearing from a single balloon. But now we have multiple balloon tests going on as well.
Very cool. So that would, I assume, like flying over Oklahoma and stuff, would be looking at sort of some of the anthropogenic earthquakes that might be sourced there. Yeah. Yep. Okay.
What are the size of these? Oh, sorry. I was just curious.
Isostatic rebound. The glacial rebound in the Midwest, is that also size detectable?
That's a good question. We haven't looked at that specifically, so I'm not positive if that would be or not. But that'd be an interesting use case.
Sorry if you said this. What size are these balloons? Just curious.
Yeah, typically about 30 feet in diameter. So for the solar balloons that we fly, the issue flying kind of conventional weather balloons is they'll tend to pop at a certain altitude, so they'll burst when they continue to rise up into around 100,000 feet, and eventually they fail. So these are kind of the more higher end plastic balloons that you utilize, but to reduce the cost on these, we're using solar balloons, so you don't have to worry about the lifting gas.
And then how long typically would these last up in the atmosphere?
Anywhere from about 12 to 14 hours, depending upon the time of year.
And Elizabeth has a comment in the question box that says multiple balloons means a swarm of balloons that are aware of the relative locations.
That's correct. Yeah. So, obviously we already have GPS and other tracking systems on these. And so that way, where the balloons are at any given time. And we've used other ground sources as verification, typically seismic hammers or explosions at munition test sites to be able to validate these, as well as, targets of opportunity such as rocket launches, which tend to have really long infrasonic travel distances from their source sites. We're currently in the process of implementing control of those balloons, so that way we can maintain fixed altitudes and distances between a set of swarms or a set of balloons in a swarm, so you can keep a fixed constellation.
Yeah, and the swarm technology again with the more conventional UAVs and drones are definitely going to be something on the horizon as well. So that's interesting to see you working on that technology with the balloons and the seismic sensors. Does anyone else have any thoughts or comments on just kind of novel sensors that are on the horizon or sort of non-conventional platforms for drone geophysics?
So you mentioned have you tested these sensors on normal UAVs? Just
we have, but again, you can filter out the noise that you get, because you do tend to get a pretty broadband set of acoustic signatures coming off UAVs, and while they tend to be in the high frequency, you also get some lower frequencies as well, and you can filter those out on these sensors. So if you are looking or trying to use this, for example, for some seismic testing, then there's some potential applications there as well.
So a question just came in the chat. Does anyone know the status of drone gravity? Good question. Yeah, I still think that's in the research and development stage. But I don't know too much.
Yeah, my general understanding of it is that it's rather challenging just due to some of the corrections with elevation. Obviously, like anyone knows that if you're running the gravity surveys, the distance you are from the ground and how well you can precisely determine that is one of the limiting factors with drones for being able to run precision gravity surveys. I know from my magnetic surveys, even like back in the beginning in 2016, the limiting factor again then, even for the magnetic ones, was being able to determine the drone's elevation to a very accurate level. So I think that's going to be one of the major challenges with moving drone gravity forward. Elizabeth says Centrix is working on it, and I don't know if there's anyone from Centrix here, but yeah, that's a great area of research that I think will be coming along in the future.
I have a question for Jamie. Jamie mentioned remote ID and how that makes beyond generalized sight easier. How does that solve the risk mitigation questions that the FAA has? So you have remote ID, you still also have to have detect and avoid, and you have to meet your ground risk mitigations. So
Yeah. I had to be careful in what I say about that. I wouldn't say it necessarily makes it easier, but it's a necessary component for the unmanned traffic management system, right? And that stuff is still not just being baked, but the recipe, for whatever that cake is going to look like is still being determined. So, a lot of questions, not just in the US, but also, globally about what that, those DID systems and, overall unmanned traffic management components, going to look like. So I have to be careful not to misstate. I think, remote ID is going to be useful to some degree, but it's still not going to solve all our problems.
And I guess with relation to remote ID, how much punting do you think the FAA is going to do on that, given the fact that there are 0 providers out there that have a solution to that problem?
Yeah, that's a great question. And I was at a FAA meeting in DC at the Beyond for the Beyond test sites week before last. And, there were a lot of questions that came up on that. And I would say, maybe different answers depending upon who you asked at the FAA. So I think that is also still TBD. I wish we had a definitive answer right now and be able to say, yes, this is what we can do and can't do. And this is where we're going in the future with our true timeline, right, in terms of what that's going to look like.
Excellent. I believe Ed commented, by the way, just going back to gravity systems are now being flown on UAVs. That's good to know. We'd love to hear about it. Maybe submitting talk. Get that out into the public. A couple of more questions. Can satellite constellations be used to replace cell phone and radio communication to the drones? Is it feasible and economic?
There's a cheaper and more stable methodology. If you were interested, come talk to us. The SATCOM, I don't know if anybody else here has used SATCOM. Honeywell has a system, but the Iridium network has immense latency, and it gives you very, very lean telemetry. So if you want any other data from the drone, it's going to be way behind. Your signal priority is behind everybody else who's using that network. It's heavily oversubscribed. The SATCOM thing, if you have an unlimited budget and a very large platform, the antennas are pretty large, then go for it. And this is where it potentially makes sense to have like Florida Power and Light just had their FPL Air 1, which is effectively just a experimental aircraft that they took the pilot out of. That's the size and scope of equipment that you need to support SATCOM. But on a light UAS, pretty much your only option is these Iridium chips, or maybe some small box satellite provider, but your latency is going to be bad and your throughput's going to be very bad. Cellular is what Kim talked about, and maybe she can talk more about that. But if you have good 5G coverage, go for it. But where we operate, it's not an option.
And what is the current, this is just another question, what is the current development of active source EM beyond metal detecting? How high can one fly with size and weight limitations? Anyone want to comment on that? Or maybe we'll leave that till maybe we could talk about it after Ron's talk on EM61. All right. I think that's all the questions that have come in. Just check the chat.
Hey, Laura, I'm not sure if this goes to the question that was just asked. I know that there's a lot of research that's being conducted in locations of like well casings and things like that, subsurface. And so we get a lot of requests specifically from some of our Department of Interior brother and sister agencies on detections of well casings specifically. So can't say that we are in an operational capacity to do that, but we have explored the use of the technology for identification of those casings.
I'd like to add a little bit related to the cell phone and some of the coverage question. I don't quite see it on here. Just trying to scroll to it. There's about $65 billion in the infrastructure bill that will be used towards broadband. All of that won't be necessarily, some of that will go down to individuals and urban and residential, but some of the discussion is about how to connect rural areas to broadband and have access to services like 5G. That's going to be incredibly challenging because a lot of rural areas are still using even satellite, but at a very slow speed. So there may be some opportunity to continue to build out that environment as it relates to cell phone usage and broadband as that funding becomes readily available, and we look to connect the rural areas more to suburban and urban in terms of speeds and connectivity. That will help drone operators who are working in those areas where there's currently very little coverage or nothing that's incredibly reliable at this time.
Yeah, that's very promising. Great. There is another question that came in. Is there any research being done on using a second drone to maintain line of sight and enhance communications with more distant drones?
Yes.
We've done that in the past for some tests in restricted airspace. So it is possible to do that and extend the line of communication, using that middle drone as a bent pipe. So particularly useful as you go over, if you're trying to do line of sight communication and you're still restricted in altitude, to be able to have, drones in the middle to be able to handshake those communications. As far as I know, most of those tests current tests in the NAS are really focused on higher altitude systems like Atmosats, to be able to do large scale kind of broadband communication for emergency response, such as in disaster zones. Skydweller is a company, for example, that's doing that using high altitude solar powered aircraft. And I know things like, some of the other solar powered aircraft projects are really kind of focused on that.
Yeah, in the Department of Interior, we have experience doing very similar missions within the wildfire program to extend beyond visual line of sight missions due to topography mapping and things like that. So we do have some experience in those operations.
And we have a open source solution specifically for that that is very stable. And if you're interested, just come reach out to me and I'll talk to you about actually how to pull it off.
Excellent. Yeah, which brings you to the point. There should be contact details for all speakers and panelists in the program. And if there isn't, we will follow up. I believe someone pinged me that a certain contact was not there. So this is, I guess, a more geophysics question. What is the status of drone time domain EM and EM surveys on mineral exploration? Don't know if anyone wants to comment on that, or we save that for some EM talks. All right, well, thank you so much, everybody. If the panelists can stay on for the discussion, great. And then there'll be a chance to ask further questions. So that's the last hour of the day. To talk about any of the talks or anything we talked about in the panel. Callum, anything else you want to add?
Nope, I think that sounds good. Yeah, we'll definitely touch on more of the EM topics later on with some of the other speakers we have. So maybe they can talk more specifically to time domain EM and just EM surveys in general. But no, this sounds good. And yeah, everything is looking great.
Yeah. Thank you so much to all the panelists who came on. That was a really interesting discussion. Just learning so much about what's happening with drones, and hopefully everyone on the call got something from that discussion.
Well, welcome back everyone from our 20-minute break following the Drone Geophysics Innovation Panel discussion this morning. I'd like to once again thank all of the panelists for joining us. It was a very insightful discussion on the future of drone geophysics and where we might see this going. We'll now be transitioning into the technical talks as part of this conference. As was mentioned this morning, please type any questions you have throughout the presentations in the Q&A tab, where Laura and I will attend to them at the end of the presentations. Any questions we don't get to in the live setting will either be answered by the presenter after their speaking time, or will be brought forward into the discussion at the end of the day. Now, however, we have a 10-minute virtual demonstration from Josh Sellers of Seequent, one of our platinum sponsors for the event. Josh is a geophysicist specializing in geophysical processing, interpretation, and geological modeling for exploration and feasibility studies of geothermal and hydrocarbon resources. He holds a bachelor's degree in geophysics from Memorial University and joined Seequent in 2017. Josh's demonstration will overview the classification of magnetic domains using machine learning on UAV magnetic data collected over the Crayston crater. Josh, please take it away.
Thanks, Colin. Great introduction. You actually covered a lot of what was on that first slide, which is great. So good morning and afternoon, everyone. Thanks for attending the 2022 SEG Summit on Drone Geophysics. Obviously, my name is Josh Sellers, as Callum just mentioned. I'm a project geoscientist based out of Vancouver, Canada, with Seequent since 2017, mainly specializing in energy exploration feasibility studies. So today, what we're going to do is we're going to explore how to automatically classify magnetic domains using machine learning on UAV magnetic data collected over the Keystone crater. So just a little bit about the company. Seequent is now a part of the Bentley Systems group of companies. Bentley is an international infrastructure engineering software company that deals mainly with the surface or built world. Seequent is the Bentley subsurface company, dealing mainly with the uncertainty below the ground through processing, analyzing, and interpreting geoscience data. But of course, we don't treat the subsurface in isolation and aim to bring it together with the digital understanding of the built environment for a combined, holistic view that crosses the soil structure interface. So the Seequent subsurface solution portfolio provides tools to work with geoscience data for mining, civil, environmental, and energy exploration and production. Through our cloud-enabled model, we'll create holistic subsurface digital twins to visualize, integrate, and manage our geoscience data from a centralized, auditable environment. Getting more into the geoscience side of it and the technical aspects, we have a UAV geophysics extension in Oasis Montage that enables rapid survey planning and processing of UAV magnetic data. And this includes the ability to subdivide your survey areas based on your drone flying range while remaining compliant with local visual line of sight requirements, which is obviously quite a hot topic in the panel discussion earlier. We also have the ability to remove discontinuities, so do some pre-processing, filter velocities, and apply base station lag and heading corrections. We can also effortlessly remove extraneous data and merge sorties into a single continuous line across the area of interest. Obviously, one of the main challenges with dealing with drone magnetic data is to combine those into a continuous survey line for additional interpretation work, similar to what we see in the bottom right-hand corner of the grid there. We can also automatically compare and adjust magnetic field values from tie and survey line intersections to minimize the differences, and then seamlessly integrate that UAV data with supplementary geology and geophysical data in 2D and 3D. So how can we use our UAV magnetic data to provide additional insights into the subsurface? On the right, we have a high-resolution UAV magnetic data set collected by Ron Bell of Drone Geoscience LLC, a globally recognized pioneer in the use of small UAS to collect geophysical data. The data was collected over the Keystone crater in the Northwest Great Sand Dunes National Park outside of Keystone, Colorado, using a geometrics UAV-enabled mag arrow over an area of roughly 240 meters squared. All of the processing of this data set was completed in Oasis Montage using the UAV Geophysics extension. And on the left, we have a digital elevation model gridded from high-resolution elevation data, which represents the outline of that crater or crater-like feature. We can begin to visually correlate the magnetic highs in the gridded data with the rim of the crater-like feature from our DEM. However, there are many more tools at your disposal in Oasis Montage to provide additional insights into the subsurface. One of these tools is the magnetization vector inversion, or MVI, enabled through Voxy, a cloud-based geophysical inversion accessible directly from Oasis Montage. So rock magnetization can be thought of as a collection of oriented magnetic dipoles, where conceptual or conventional susceptibility models assume all magnetization is from the inducing field and fails to account for demagnetization, anisotropy, and any other effects related to remnants. MVI recovers not only the amplitude, but the direction of magnetization. This can provide insights about the rock forming processes and alteration of the subsurface, including any potential remnant magnetization. To prepare for our MVI inversion, our data was decimated to one sample every meter, where our total magnetic intensity and location information were inverted for the amplitude and direction of magnetization in 3D. The MVI produces a vector voxel, which represents the magnetization of the subsurface in the X, Y, and Z directions. This allows us to map subsurface magnetization in a different way, not only a scalar amplitude, but a magnetization vector. We can use the spatial and data clipping tools available in the Oasis Montage 3D view to manually group vectors with similar properties to begin classifying the subsurface into magnetic domains. Magnetic domains, in this case, being areas with similar amplitude and direction of magnetization. Alternatively, and more efficiently, we can use unsupervised machine learning to automatically classify or group data with similar properties in 2 or 3 dimensions. With Python's support in Oasis Montage, we have the ability to take advantage of vast open source scientific libraries. In this example, we'll analyze the results of the self-organizing map run on our MVI inversion. So one of the main objectives of machine learning is reducing the dimensionality of our data. In other words, we can provide many inputs, that's high dimensionality, into a self-organizing map and create a single output classification in 2 or 3 dimensions. Self-organizing maps are an unsupervised classification technique used to analyze and visualize high-dimensional data based on the principles of measures and vector quantization. Unsupervised learning is a type of machine learning that looks for patterns in data, in this example, geoscience data with no existing labels or human supervision. Self-organizing maps lend itself very well to geoscience data analysis because often, as is the case here, we have limited information about the geology, geochemical, or physical rock properties of the subsurface. And this actually touches really well on one of the panel discussions that Tim and Roger discussed about the machine learning aspects of high volume drone geoscience data. The self-organizing classification dialog can be run directly from Oasis Montage after installing Python and downloading the self-organizing maps menu, where we can automatically classify each cell of our vector voxel based on the amplitude of magnetization in the X, Y, and Z directions. The resulting voxel has 32 distinct classifications, each represented by an explicit color. 16 base or background classes represent the non-anomalous vectors in colder colors, and 16 anomalous classes defined by the anomalous 10% in hotter colors. This reduces the dimensionality of our input data and automatically categorizes vectors of similar properties into groups, which can be interpreted as separate magnetic domains. This provides insight into the physical distribution of rocks with similar properties. So as expected from the input magnetic data, the crater itself is anomalous. Using the spatial and data clipping tools, we can compare the amplitude and direction of magnetization of the area under the crater to the background geology. Noting the shallow area under the crater is classified as anomalous based on the results of our MVI and subsequent SOM analysis. We see the high amplitude vectors are almost solely confined to the area under the crater. And using the directional filter, we can manually determine the main angle of inclination for each of our magnetic domains. And as we progress through the inclinations, we can see that little to none of the crater is within 10 degrees of the IGRF inclination angle. So in the past 10 minutes, we covered a lot of ground. We went through the planning and processing steps of UAV to prepare the raw data for advanced interpretation. We then reviewed the results of an MVI, which recovered the amplitude and direction of magnetization in the subsurface, then automatically classified the subsurface into magnetic domains using SOM analysis. So what are some of the key takeaways from this exercise? Little to none of the crater is within 10 degrees of the inducing field based on the results of our MVI, meaning rocks in the crater may have remnant magnetization or undergone some other rock altering process. The crater itself is split into different anomalous magnetic domains, particularly the boundary of the crater. Mixing the crater and host or background rock would cause the yellow-orange portion on the edge of the crater, and the depth to source could be very shallow. So thank you all for attending, and that is the 10 minutes.
Thank you very much, Josh. That was a fascinating talk. I really found it interesting how you can determine, with the software there, how you can outline the crater specifically with the physical properties. That's amazing. We'll now be moving on to our keynote speaker, our first keynote speaker. So Josh, if you could unshare your screen, and we'll try and get Timothy to be able to share his screen, and I'll give him an introduction. So our first keynote speaker of our technical session today will be Dr. Timothy de Smet. Timothy is an assistant professor in the Department of Geological Sciences and Environmental Studies, and is the director of the Geophysics and Remote Sensing Laboratory at Binghamton University in New York. His area of expertise include aerial remote sensing and near-surface applied geophysics. Dr. de Smet will give a talk on UAV-based hydrogeophysics. When you're ready, Timothy, please take it away.
Pretty much what I'm going to be talking about is UAV-based hydrogeophysics. And I'm going to be talking mostly about a couple of case studies from some of the research that I've just kickstarted here in New York on harmful algal blooms in freshwater lakes, specifically the Finger Lakes, and then submarine groundwater discharge from plumes on Rapa Nui, and that's Easter Island, so Chile, although it's really in the middle of nowhere in the ocean. Harmful algal blooms, just to kick it off, they occur when blue-green cyanobacteria containing toxins produce an algae that grows out of control in the ecosystem. So they create this eutrophication. This is largely due to anthropogenic influences like warmer waters. Obviously, there's climate change, but also inputs in terms of nitrogen and phosphorus from agricultural runoff and from cattle grazing, things like that. Now, before we move on to the next slide, I like to kind of use my professor soapbox. Why should we care that harmful algal blooms are creating eutrophication and going on and creating anoxic environments that are killing fish and other species? Why does this matter? In terms of what's actually happening, harmful algal blooms are obviously, they're an increasing threat to freshwater quality, to public health, and to aquatic ecosystems. So the ecosystems, it's really a systems perspective, right? So if you lose one species, you really can potentially have problems for a cascade effect. Obviously, the freshwater quality, a lot of people don't realize this. In terms of the quality of the freshwater, a lot of times the treatment facilities are right there on these Finger Lakes in New York State. And so it's increasing the cost. And then it's having really bad negative consequences in terms of the economy. It costs the economy of the world billions of dollars a year in losses to tourism and fisheries. So it's a problem that really needs to get solved sooner rather than later. So I'm having a little bit of latency between me moving forward on the screen that I have in front of me and then the one that I'm talking on, but it's all good. So how are harmful algal blooms currently studied? In terms of the current methods of studying harmful algal blooms, most of them are going to be satellite-based remote sensing. Now, what I'm going to be talking about mostly is UAV-based remote sensing. So satellite-based remote sensing is going to have a number of key drawbacks compared to UAV-based remote sensing. Now, UAVs also have some drawbacks, and we'll get into that as well. So when we're talking about satellites, and when I talk to my students, I always talk about three types of resolution. There's spatial resolution, there's spectral resolution, and there's temporal resolution. So in terms of spatial resolution, satellites are going to have much coarser ground sampling distance or pixel size when you look at it. So it's great for imaging things like the ocean, but terrible for things like ponds and lakes. In terms of the spectral resolution, satellites and sensors like the Parrot Sequoia or any of the MicaSense sensors, we're going to be talking about bandwidths anywhere from like 10, but generally not, more like in the tens of nanometers to hundreds of nanometers. So pretty wide bandwidths. Whereas when we're talking about, sensors that are hyperspectral instruments like the one I'm going to be talking about today, we're talking about bandwidths on the order of like 2 nanometers. We're talking about collecting like 150 bands between 400 and 1,000 nanometers. So really, really great data sets. And then in terms of temporal resolution, obviously satellites like Landsat 8, you've got a revisit time of 16 days. Sentinel's a little bit better. And there's some new satellites going into orbit, but the revisit time for UAVs is on demand. You can put a drone up in the sky anytime you want to and fly. Now, those are the positives in comparing UAVs based on spatial, spectral, and temporal resolution with satellites. Now, what's the downside to that? the data sets are freaking huge with these ground sampling distance. So 15 minutes, so every minute that you're up in the air with a UAV-based hyperspectral instrument, that's 10 gigabytes of data. And that's the raw data. That's before non-uniformity correction. That's before you start taking it and making these enormous data sets that then you're going to have to do principal components analysis. Like we were just talking about data reductionality and things like that. There's just a lot. And every time you process it, you're essentially like quintupling your data set. So I have a network attached storage drive that has over 30 terabytes of data. So there's problems with that, with data handling, data storage, data processing. And then the other problem is obviously that you're not going to be able to cover as wide of an area. A satellite has a huge swath width. The swath width when you're flying at 400 meters AGL with this guy is, more on the order of like, 100 meters. So the amount of area that you can cover is necessarily going to be smaller. Also, you want to be flying around, solar noon, which is really gives you like a 2-hour window to get really high quality data at any given point with a hyperspectral sensor. So in terms of what I've been working on, I've been working on testing the efficiency of these new UAV-based hyperspectral sensors to detect and monitor HABs, to develop cyanobacteria and chlorophyll A reflectance algorithms based on a comparison of UAV-based hyperspectral imaging, and documenting the duration and magnitude of HABs on lakes like Chautauqua in New York State between about May and October, which is the season where we have harmful algal blooms, and developing best practices for the use of harmful algal blooms. So in terms of developing best practices, what you have to do is you have to obviously have calibrated reflectance cards, and MicaSense makes decent ones that you can use with either the Parrot Sequoia or any of their new MicaSense cameras. But then there's also going to be things that are like pretty standard, like Y-balance cards and Kodak Ray cards, things that have existed for just ever, that are pretty spectrally flat within the visible light. In terms of the flights and how we're flying, the flights are going to be really relatively low in altitude. I tend to fly about 50 to 100 meters. And then for some really, really high resolution stuff like unexploded ordnance, I'll fly even lower. I'll fly at like 10 meters. You use automated mission plans, but one of the problems is that a lot of times we're flying in areas where the vegetation is so large. This video is playing pretty slow, but the vegetation is there in such a large way that you actually have to manually take off and land and then start your waypoints after you've kind of gotten a little bit away from the trees, which is fine, but it's just, it adds an extra little step that's kind of a pain. And then, you have to have your graduate students there holding the tough book while you're, flying with the RC. Except for some of our graduate students are actually pretty good at flying too. So I let them do that every now and then. In terms of what happens after we collect these pre-planned, autonomous missions, we're going to be looking at these data and quantifying chlorophyll A content with a fluoroprobe, which is pretty much New York State DEC's standard. So in terms of data processing, a lot of the stuff in terms of like the kind of Landsat and the satellite stuff, you can do either like in Google or you can do in ArcGIS programs, QGIS, anything. With the hyperspectral data, I've mostly been using Harris Geospatial's ENVI software, largely because it's pretty easy to teach students. In terms of some of the results that we have recently from Canandaigua Lake, we've noticed that there's going to be spectral peaks that people have noticed from satellite data at about 710 nanometers for harmful algal blooms, but other things that are chlorophyll producing, like lily pads, are going to be producing spectral peaks at 740 nanometers. Which is great. That means that we can differentiate harmful algal blooms, presumably from other chlorophyll producing things. The pixel size is huge, as you can notice here on the slide, from Landsat 8 data, 30 meter data versus a couple of swaths from the hyperspectral camera. And when we looked at these, we actually found that we're going to be slowly but surely able to hopefully quantify this better in terms of creating some sort of algorithm that'll probably be regression based to quantify chlorophyll A concentrations from reflectance. And these data show that they're, when we actually analyze them under the microscope, we've got microcystis. So in terms of depth of investigation, that study made us kind of think we need to start thinking about some other things. So this is some pretty high resolution data. We started creating these like little ramps where we have colors on the ramps, alternating color bars. And we wanted to see how deep we can see even in a bloom. So as you can see, it looks kind of greenish. It's because that's like about 50 micrograms per liter concentration of cyanobacteria in terms of chlorophyll A producing cyanobacteria there. And so we wanted to see if that affected anything, and if there is actually some depth of investigation that we're looking at, and therefore we should potentially shift our sampling strategy from a water sampling perspective. Should we just be skimming the top, or should we be taking more of a water column? And it looks like we probably, for the smaller areas, in terms of concentration of harmful algal blooms, we should probably be collecting more of a water column. So the future of the harmful algal bloom stuff, we're going to continue to gather hyperspectral data sets coincident with satellite data. We're going to continue to build our database of ground truth samples to build a better algorithm to convert these reflectance values to chlorophyll A concentrations. And then eventually we're going to try to work on, once we have that sorted out, machine learning based hyperspectral unmixing algorithm. And then recently, and you'll see Jasper Bauer in a few days presenting on some of this stuff, we were out at CENFEX at Oklahoma State University collecting a bunch of UAV based data that was hyperspectral, thermal, multispectral kind of visible light stuff to try to detect unexploded ordnance. And if you look over here on the right, if you fly really low with hyperspectral cameras, you can actually see tiny landmines like the PFM1 that's only about 10 by 4 centimeters. So the future for hyperspectral research goes beyond hydrogeophysics. Easter Island is another case study. So we're moving on from harmful algal blooms, so environmental remediation, to another type of environmental remediation. So Easter Island is pretty much about as far away from anywhere as you can get. Rapa Nui means the navel of the earth. And it's insane when you fly there. And when you're flying over just swaths of ocean with no other landmass, to realize how far you are away from anything on the planet. Its closest continental landmass is 3,500 kilometers away, and that's Chile, which is it's a part of. And then Pitcairn is the closest other island landmass, and that's over 2,000 kilometers away. So here's a picture of Rano Warukau, which has a volcanic cinder cone that sometimes has a lake, but it's been dry the last couple of years. And I would say that everyone should go there at some point in their life. It's like walking into an M.C. Escher painting. It's nuts. So in terms of Easter Island, why am I there? I'm doing preservation archaeology, creating 3D maps of moai statues and ahu and things like that. I'm doing storm risk and damage assessments, so for future hydrogeological events, but mostly for a groundwater coastal seep survey. So in terms of the looking at storm risk and damage assessment, there was a big storm there on May 28th that actually damaged a fair amount of the ahu platforms that contain the moai and then their little top hats, the pukao, out of the red tuff. And what's happening is they're eroding these out. And in fact, some of the moai too have fallen into the ocean relatively recently. They're all built right there on the ocean. So we really, really need to be careful about our damage and risk assessment, and how we actually look at this island. I recently came out with a pretty cool paper with some of my colleagues. Terry Hunt, he's Dean of Graduate College over at the University of Arizona. Carl's the Dean of Research here at the BU, and Bo is a recent PhD student that I was working with. So in terms of the island, there are 4 potential spots where we can have lakes: Rano Kau, Teravaka, Rano Warukau, which I was just talking about, which is the quarry for the moai, and Poke. Now, this is an image of the crater at Rano Warukau from May 2019 when I was collecting these data. It's completely dry. Rano Kau, which usually has the deepest lake, almost completely dry. You can stand in it. It's nuts. Easter Island is forecast to be in a 100-year drought over the next 100 years due to anthropogenic global climate change. The seawater is also predicted to rise on the island 2 meters, which could inundate a fair amount of these ahu platforms and the moai on the platforms. The other thing that's really happening there is tourism has changed. Obviously, COVID put a dent in tourism, but from about 20 years ago to now, they went from having an average of about 15,000 tourists to about 150,000, so an order of magnitude more, and they're just drinking more water. And so what's happening is the recharge rate on the island is not meeting the recharge rate necessary to meet both the island's population and the tourists. And so what's happening is we're getting more brackish water, which is obviously a bad thing, and less fresh water. So we need to start thinking about how can we find new sources of water on the island, or how can we try to help conserve sources of water on the island? And so what we started doing was this coastal seep survey. So here's an example from near Ahu Vayu. On the right is the raw thermal data as it's being collected. On the left is a processed orthomosaic. As you can actually see, there's Ahu Vayu and Ahu Terakau. These settlements were placed there by the people, the prehistoric people, the Rapa Nui, for a reason. They were placed there because they had these freshwater plumes that are talked about by European explorers when they're like, they say things that are like super racist, like the natives would slack their thirst with brackish water, things like that. But really, actually, the natives had this great knowledge and they knew where all the freshwater seeps on the island were. So they weren't eating, drinking seawater. That's stupid. They would have went extinct. They didn't go extinct. That shows how resilient and sustainable what they were doing was on the island. And so all of these areas where we have these ancient settlements and where we have these Ahu, so this is Anakana Beach. It's the only beach on the island. So like, if you go there to travel, realize there's only one beach. You're gonna see it in all the pictures, but that's it. So this is Ahu Nanau. And what we can actually see is we can see the freshwater coming out of these seeps, both in real times with our eyeballs from a visible light perspective, but then we can also see it as this cooler fresh water going into the warmer ocean water. Yet again, where we have these Ahu and these settlements. Just west of Anakana Beach, there's Ahu Te Ipu. And then again, it's the same thing. In fact, there's a well there. There's a modern well there that would have been probably an ancient well hundreds of years ago collecting fresh water. So the people on the island realize this now, and they obviously knew it in the past. Otherwise, they wouldn't have survived. It wouldn't have been a sustainable environment for them. In terms of some other sites, here's La Perouse. You can actually see our boat that's collecting our salt data, our electromagnetics data, is actually pulling out, and you can see that it's cutting through this cooler water. So there's tons of evidence, and then we have the electromagnetic data on the right that confirms this. Ahu Te Pitukura also has a number of these freshwater seeps. In terms of Ahu Te Peo has these seeps, and it also has these Monavai features. The Monavai features are great because they have these delicious little bananas that you can pretty much only get on these tropical islands now that don't exist. They're not like the gross, disgusting giant bananas we get from the grocery store. The small seeps also tend to be towards these giant Moai roads, as you can see here at Ahu Papa Tekena. And a lot of other features on the island can be seen with these types of thermal surveys. And in terms of the built environment on the island, it's pretty much an ankle buster. It's basalt rocks, but the basalt rocks were actually anthropogenically created to create more biologically available nitrogen and phosphorus, which I find to be really cool. And when you go there now, you can actually see plant species that are related to cultivation. So it's pretty amazing to see the environment there and how sustainable it was through time. In terms of acknowledgements, obviously I got to thank the audience. Thank you for listening to me ramble on about drones and hyperspectral cameras and harmful algal blooms and Easter Island stuff. New York State Department of Environmental Conservation, the United States Geological Survey, they gave us a generous grant, and Corning for their generous donation of hyperspectral imaging. And I'd also like to thank Mahanua, which is the Cultural Resource Agency on Easter Island. So thank you very much for listening to my talk. And hopefully there's some questions, even though there's no time, later in about an hour when it looks like there's more Q&A.
Yes, excellent. That was a really fascinating talk. Thank you very much, Timothy. In the interest of time, we won't take any questions live now, but if you do have questions, you can put them in the Q&A and we'll either address them later on in the discussion, or Timothy can type answers in the chat as we move forward. One other option I was just recently informed of that we can have, if there is time at the end of the talk, there's a raise the hand button at the bottom of the screen. If you click that, our lovely SCG representative might allow you to ask a question verbally over at the end of the presentation. So those are the two ways that we can do this. For our first technical program speaker of the conference, this will be none other than Ron Bell, who is of Drone Geoscience, LLC. Ron has 30 years of experience in collection, processing, visualization, and interpretation of ground magnetic and electromagnetic data. He began investigating drones for geoscience applications in 2014, and in 2016, he successfully conducted numerous drone magnetic surveys to locate legacy oil and gas wells and pipelines, as well as to map geology for groundwater and mineral exploration applications. Ron has also played an integral role in establishing the Summit on Drone Geophysics in the past years. So I'd like to give a special thanks to Ron for that. But today, Ron will be presenting some preliminary results from a drone-enabled EM61 Lite survey to detect and delineate buried pipeline. Ron, please take it away.
Welcome, everybody. I want to thank you all for the opportunity to share my excitement about what I've done in the last year or so. I'm going to show some preliminary results. I actually collected this data towards the end of August at a site in Texas. What I'm going to cover today, I'm going to actually give a little bit of an intro to the metal using time domain EM for metal detection. I'm going to contrast the ground-based system versus the drone-based system, which has actually been one of the issues that I've had to deal with, is taking something that is pretty commonly used on the ground, often for UXO, but in this case, you're going to see that we can use it for other metal detection. And then I'm going to go through what the site was like that we surveyed it on, and give you initial results, and then discuss how I went about processing it, and then give you a look at the preliminary results, and then the interpretation and conclusions, and hopefully I can do that all within the time allotted. The basic concept of EM in general is to actually induce current flow, and in some cases you actually drive currents into the subsurface. But in this case, we're actually inducing current flow, and where there's something that's more electrically conductive, significantly more electrically conductive, such as a piece of metal, eddy currents will form, and we'll have a magnetic field that's created as a result. That is, and in fact, what we're measuring is the magnetic field response. And in the time domain, we're doing that during the off time. So the cartoon in the center is basically showing the eddy current formation from a coil that is actually pulsing the earth with an EM's signal. And then during the off time, we're using that same coil as a receiver to measure the magnetic response, or the secondary magnetic field. And we do it over here on this little cartoon in the lower left, is we're doing it in terms of a number of time gates. For those geophysicists online, this is pretty basic stuff. I'm just trying to give a background of what we're doing for those who aren't geophysicists. The sources of noise are, sometimes we have to deal with instrument noise, in this case also UAV noise. The ambient EM, that would be like the 60 hertz background noise. And then there's motion noise with the system movement, and then a bit of noise that's created by the movement of the system over terrain. Fortunately, the area I worked at didn't have any terrain to worry about. So this is a photo of a system that is commonly used. I believe this is the latest generation. It's called the EM61 Mark IIA. It's got a coil on the bottom, that is for transmitting and receiving the signal. And then there's a coil that's a distance away, in this case about 0.4 meters, that receives the signal as well. And those are helpful in diagnosing or interpreting what is in the subsurface that's causing the signal. So this is a pretty heavy outfit here. It's pretty durable. Got to hand it to Geonyx. They know how to make pretty durable geophysical gear. And when you come to putting it on a drone, it actually creates a number of issues. And so one of the first things you have to do is look at the payload capacity of your drone and ask yourself, can you actually lift this thing? And certainly I couldn't have lifted the ground-based system, but Geonyx devised a system called the EM61 Lite, and they lightened up the bottom coil, and that's also serves the same functionality. This is essentially a Mark IIA that's been created for a drone, or modified for a drone. So above it we have our receiver coil, and in the bottom coil is both a receiver and transmitter. And then up on top here, we have a thing called the Sky Hub. It's made by a company called, I believe it's now called UGCS Integrated Systems. It's SPH Engineering. They also make the Universal Ground Control Station, which is the mission planning software that that we use for planning out and executing the surveys. And they have another piece of software called Custom Payload Manager that runs and drives the 61 Lite and the control electronics through the Sky Hub, and the control electronics for the 61 is hung below the, in this case, it's a Matrice 600. And then also we have a radar altimeter that is controlled by the Custom Payload Manager and Sky Hub that we're actually using to control the altitude of the aircraft as when we're on survey. The drone that we're using is a Matrice 600 Pro. It has a payload capacity of capability of 2.5 to 6 kilograms. The difference in the 2.5 and 6 kilograms is actually due to the weight of the batteries that you might. There's two different models of batteries. We get about 10 minutes of flight time when we're putting this on survey. I first received a version of this in 2021, and I tried lifting it with my drone, and the drone complained, and it was just too heavy for the drone to lift. In the meanwhile, the Geonics did a little bit of work on updating it. They sent me a new system. I did a bunch of work on actually removing a bunch of weight from the actual system. I was able to drop it by the weight of the EM61 Life by over 500 grams, which in the drone world is a gram is weight is everything. Payload weight is everything. So we actually were hired by the Texas Transportation Institute to go down and perform some research work. When we arrived on the site, our first site was the Rellis campus, which is in the town of Bryan, College Station. This is the site managers came to us and said, well, we've got this site. We're going to be doing some construction on it. We've opened up a box and we looked down inside it. It was a concrete thing, and we realized there was probably a pipeline down below it. There was a big valve. They thought it was for this site itself was at one point started out as a U.S. Army airfield and then became an Air Force base. And then in 1988, it was turned over to Texas A&M, and that became their Riverside campus. That's when the Transportation Institute was formed. And in 2016, it was renamed Rellis. And they've been doing a lot of building and stuff on there anyway. They came to us right when we arrived on site and said, can you fly your drone with the 61 over this? We'd like to know what's in the subsurface. And so we did, based on this is, I looked down into this hole. Unfortunately, I couldn't find the photo of the valve that was there and the pipes, but it appeared to have a north-south strike to the pipeline. So the first thing I did was design a survey where I ran it east-west. And that's the green lines on this map. These are the actual flight line data that came off the drone with the EM61. So it's really using the navigation system and getting the positioning from the actual GPS systems on the drone. So we set it up as a 10-meter line spacing. In this case, I had no idea what was in the subsurface. I figured this, well, if it's a long pipeline, this is that will probably be an adequate line spacing. And we flew it at 1 meter AGL. That is, the sensor was about a meter above the ground surface. And we flew it at a rate of 1.5 meters per second. As you might imagine, that even though we were able to reduce the weight, the drone itself was still, the flyability of the drone was still impacted by the weight of the payload. And then after we got done doing the first survey, we had plenty of time. So I said, let's do another survey. and we did that one north-south. And I've got to say that was the biggest non-thinking decision I ever made. And I'll show you why here. This is the data that we acquired on the east-west site. For those who know Geosoft, you know the reds and the pinks. This is a color scale that I get out of Geosoft. I use all the time. A red and the pink are high amplitude, and the blues are low amplitude. Lo and behold, we can actually see that there is probably a pipeline running through there. There's some other stuff as well. But what I was not aware of at the time is there was another pipeline on what was the western side of the flight block. This is approximately 100 meters by 100 meters, maybe a little bit more than that. And then when we flew the north-south pipeline, a north-south survey, I'm going to refer to the east-west survey as survey number 1, and the north-south is survey number 2. We began to see some things that we weren't seeing in the first survey. For example, this feature right here that has a distinctive easterly or westerly easterly a trend to it or strike to it, and we began to kind of provide more definition on these east-west features that are in the subsurface. And we happened to fly the north-south survey, so we were on either side of on both sides of the north-south pipeline, and so we didn't really see that very well, but it does come in a little bit. And then we flew over unintentionally, actually, we flew over the pipeline that we were actually targeting. I'm going to back up a minute here and say, right there is the access point that I'm showing there that we see the valve. And okay, so I'm surprised I thought I had on there there we go. There's that access point right there. And that's where we could see it. So from the point of just having one essentially data point, which knowledge about what's in the subsurface, we were able to define a lot more within that was going on metallic wise within the subsurface. So what I wanted to kind of touch on now is that while we were in the field, this is the sort of the processing sequence that I go through, and what I had to do for this one, which I don't often do for, in fact, I haven't done it for any of the mag data I acquired, is I had to apply a lag correction, and I used that north-south pipeline right here as my point to determine what level of lag correction I needed to apply. Fortunately, we ran over it. I'm not sure how I would have done it otherwise. And then once I did the QC/QA, and then at the end of the day, we spent some time in the evening. I did a little bit more post-processing and to really try to bring together what it is we found. And this is where, I mean, I'm not actually trying to develop a finished product here. I'm just trying to get a better understanding of what to give to the site managers, what it is that we found or were detected with the EM61. That's the sort of the combination of both surveys into one data volume. And then I had to smooth it out because we had some leveling issues. So I did, and then I did an enhancement filter. In this case, it was just a vertical derivative, first vertical derivative, and I began to see that I was actually picking up a bunch of things that are in the subsurface, and this became our preliminary interpretation. The pipeline axis is where we had the valve. We think there might be an underground storage tank here. There might be one down here. This might be another pipeline. Clearly that one on the very west comes booming in. And then down on the bottom here, that might be something associated with either the sprinkling system or I don't know what else, but it's the kind of thing that this was not a part of what our work plan was supposed to be. We just got asked to do it. It took us about 2 hours to do the data collection. We were able to process and see that we had something in the field that was worthy or worthwhile continuing to to deliver to the site managers. And then I was really surprised at how much detail we were able to get out of this drone-based EM61 data set. What's next? For those who know, we just use the location points surveys from the navigation system on the drone. We actually do have an RTKG and an SS that we mount on drones. So in the future, we'll be doing that. Weight is everything. And we've been careful not to put it on and overtax our M600. And then we'll be actually working on applying algorithms. Some of them are available in the Geosoft package, or an OASIS montage. And some of them, I suspect, we're going to have to develop ourselves. But the thing is that what I was excited about, and I want to report to everybody today, is that this is a very viable way of doing metal detection for things, whether it's pipeline location or whether it's UXO. We now have a system that avoids having to have direct contact with the earth in terms, or avoids having to use a big helicopter to do the acquisition, and we can cover it. I mean, it's just relatively inexpensive in the grand scheme of things. So I thank you for listening to me. I have no idea how much I talked, but I'd be happy to take any questions. And again, thank you.
Yes, thank you very much, Ron. That was a wonderful presentation and very, very insightful. There are a few questions coming in. We'll get to those. And if anyone does have any questions, a reminder, you can post them in the Q&A, as well as you can raise your hand if you'd like to ask Ron kind of over the voice chat. So the first question we'll look at is from Anish, and it says, thanks, Ron, for the great presentation. How does the EM61 Lite on the drone signal strength compare to the ground-based EM61? Have you done any comparison of these two systems over the target?
You know, that's a really, really good question, because it really, looking at this data, kind of begs that you do that kind of correlation or that type of testing. I haven't done it so far. Do expect that I'll be doing it here within the next couple of weeks. Well, I'll be collecting some data over a pipeline here in Colorado that I know about, and I will work at running an EM61 ground-based system over the same flight lines or same traverses, so we can have a one-to-one comparison. I'm hoping to be able to present that in the spring.
Yeah, I think that will be a very, very interesting case study to look at, to compare the ground-based EM to the potential of drone-based EM. Excellent. Second question for you is, how high can you fly before losing sensitivity? If the site is covered in tall trees, will this work?
If you're looking for cars on the surface and you're flying the EM61 over the trees or the bush to try to identify those cars, I think you probably still would be able to detect the cars. If you're looking for things that are buried in the subsurface, like a pipeline, one of the tests that I'll be actually conducting in a couple of weeks is just to do an elevation test, how far away I can get from the pipeline before it becomes undetectable. And I haven't done that yet, but it's in the cards. It will happen. And if you want to, you can see on the screen my email, and you can always reach out to me, and I'll be happy to share what it is I'm doing or what I'm learning about flying this EM system. There's a number of issues. The UXO community has dealt with a bunch of them. I haven't done much UXO, so I'm actually working with reading the literature and trying to apply what I've learned out of the literature to what I'm doing for a different problem. This is the pipeline location is a different problem than UXO. I know that's a long-winded answer. I really don't. I hope to have an answer to that question here within the next couple of weeks.
Yeah, no, lots of interesting research to be done with this, and we look forward to your results. Another question, this time from Elizabeth, says, which channel of the EM61 did you use to grid and process the data?
What you're looking at is channel 1. And Elizabeth, you know that there's 4 channels to this thing. Channel 1 has the highest amplitude, so that was the one I started with. Just all of the channels need to be looked at. And also, in my mind, all of you need to develop a way of determining the rate of decay, and then tried that, use that as maybe a bit of diagnosis or a bit of, I'm hopeful that we could actually say something from the rate of decay of the signal, but I haven't done anything where I can actually prove that that is a useful parameter.
Thank you. Another question we have says, thank you, interesting result. Up to which depth can you get reliable data with this system?
That's a good question. I don't really know how deep this thing will actually see. I was very surprised at the amplitudes that I actually got in channel 1. And so when I get back out in the field to test it, and I'll do sort of a offset, ground offset test, I'll plot it up, and if anybody wants to see it, I'll certainly email it to them. And just to get that will be the first order of actually determining what kind of depth of exploration you have with this system. At this point, I don't know.
A question from anonymous attendee says, hi Ron, have you looked into any other UAS platforms besides the Matrice 600 with the EM61 Lite, recommended platforms for federal work in the US?
I am looking at that right now. I'm working on taking this system to California to fly it on the Perimeter 8 made by Skyfront. And what the advantage of that system is, it's US made. I don't know if it's on the blue list, but I do know that it has longer duration flight times and a bit better payload capacity. So I'm going to go out there and I'm going to lift it, and we're going to fly over one of their test areas, which I've been on before, flying the magnetometer, flying the mag arrow over, and I know that there's pipelines there, so I know I have some targets to actually map. So that's one. That's made by a company called Skyfront. And then I've been reaching out to various other heavy lift manufacturers in the US, and with the idea that I'd like to take this to them, and we do a little bit of lifting with it and see what it would take to. The DJI Matrice 600 was a pretty easy mount, but I did have to fabricate some material to actually reduce the weight of the. I had to fabricate a mount, but then I also had to replace the box that the electronics module comes in, and through that and through other things, I was able to reduce the weight by over 500 grams, which is pretty. I was surprised that I could do that. I could actually get it down to where the system doesn't complain when you're flying. So
always a fun challenge for sure. Okay, we have quite a few more questions here, which we'll continue to go through. Question that says, what flight speed did you use, and kind of so that the drone can maintain altitude based on the altimeter data?
There's actually two questions there. One is, what is the sampling rate of the altimeter beta, and how is it controlling the drone? We often fly at 10 meters to 15 meters per second with the altimeter. And it seems that, but we're not flying at 1 meter above the ground surface. We're flying it up at 15 or 20 meters. And it seems to do an adequate job of actually, this is for mag surveys, generally we're doing it for well locates. That seems to be doing an adequate job at that speed. So I don't think it's the actual sample rate of the altimeter. Now, when we flew this one, we flew it at 1 to 1.5 meters per second. And the reason we did is that allowed the drone to not be overwhelmed by the payload. We think of the fact that we have a pendulum, a heavy weight that this thing is hanging below it, below the drone. It's putting forces on the drone that the drone doesn't really like to have. And we've lifted, I've used a Matrice 300 to lift the mag arrow, and that has a much lower capacity. You can still lift the mag arrow, but it starts to go kind of weird once it gets that pendulum starts to go with the payload. So one of the things that had occurred to me in the last 5-6 years was that two things that occurred. One is that almost all drone pilots are never really taught how to fly a payload where you have a slung load. And so one of the sort of initiatives I'm working on is actually working with a local community college to develop a training program to train drone pilots how to fly slung payloads. A lot of the geophysical sensors that we use, they by necessity, they have to be slung payloads. This is a good example. You can't, in order to be able to make the measurements, you gotta have the separation of the coil from the drone. I mean, the sensors from the drone. So the answer, hopefully I carried on, but hopefully I answered your question.
Yeah, no, that's great. And I think that segues perfectly into moving on to the discussion section, where we kind of open up the floor to all the participants to ask sort of questions to any of the presenters throughout the day. And we will end the day now with this discussion section. We'll continue to go through the questions that are posted in the Q&A as well. We can read through those, and people can unmute themselves and ask questions as they see fit to things. So as we start moving towards that, I had an interesting question just regarding kind of my own research in this area on the magnetic interference and electromagnetic interference of drones and kind of the setup you're using. Did you notice any sort of character that was picked up by the EM61 of the drone interference, or was the suspension length that you used far enough away?
The field that is produced by the coil, the transmitter coil, does mess with the aircraft. It messes with the electronics of the aircraft. So what we ultimately had to do is develop a field procedure where before we lifted it, we actually had the drone above the sensor, the transmitter, far enough so that the amount of interference that was causing to the aircraft electronics was minimized.
Mm-hmm.
And that seemed to work okay. But it meant that we had to take another point of view in terms of we for a lot of our surveys, a lot of our systems, the magnetometer, for example, you could just leave the drone on the ground and then lift it up, pull out the payload below it, and then fly off and do your mission. In this case, we had to have everything, the drone far enough above our transmitter that it no longer was an impact. Now, that was one question. The other question is, do I see the impact of the drone itself on the data that I'm acquiring with the 61? And so far, I haven't recognized that at this point. So, and that could be just because of sample rates, could be because of sensitivity of the receiver, could be the distance away from the drone itself. But the big issue that we found is when this thing's pulsing, it basically limits the ability to fly the drone. So.
Interesting. Yeah, I guess it kind of acts like some of the technologies that basically pulse, signals towards the drones to bring them down in kind of the defense sector and stuff like that. And that's something, I guess, with active sensors, we're going to have to be mindful of moving forward with placing them on drones. So that's really interesting.
Yeah, it is. And when I'm going to kind of address one of the questions that was asked earlier about what is the state of time domain EM in the drone business. Well, the state in terms of active systems for metal detection is that there is at least one that is able to go out and be able to fly these things. There's probably others, I just don't know about them. But what I do know about is I do know of 4 semi-airborne EM systems. And one of them is working in the frequency domain. That's made by a company out of Germany. Another one is working in sub-audio magnetic domain. And that's an adaptation of a helicopter SAM system that a company called Discovery Geophysics is actually put on a drone and is working on implementing that. Then there's another group I just learned about. I forget the name of them. They're in Canada. They're making an audio frequency EM system, and I've been told, or at least given the impression by the guys at Geonics, that they're looking at building a drone-based time domain EM system. I hope I get the opportunity to work with that, but so at least there's 4, and I suspect that there's a few others out there that just aren't mostly applied to mineral exploration, that just haven't come to the surface yet.
Thank you for the answers there. That's awesome. Okay, I think we will transfer into the discussion section where everyone will be able to be brought in. Laura, did you have anything you wanted to add before we go to that? And then I can continue going through some of the questions that were asked, or people can ask them themselves when they're unmuted. Perfect. Well, while we are doing that, I will ask the question from Tyler to Ron. It says, "Hi, Ron. Are there any current systems that put the EM transmitter and receiver on 2 different drones to increase depth of investigation and play with the spacing?"
I personally don't know of any at this point, but with the ability to do swarms and maintain pretty precise positioning of the navigation and positioning of the drone, I think it's a great idea. I'd love to work on it.
For sure.
Yeah, more technical challenges.
Yes, exactly. A question from
So the answer to the question, did I estimate the depth of the burial? Not yet. It's definitely in the work plan. It just wasn't, I just haven't had the time to get it done. What is the minimum flight speed?
Yeah, what is the maximum flight speed to record
I
data?
think that's right now with the EM61, because of the weight, we're keeping it at about 1.5 meters. So if we didn't have the weight, either by not having the weight constraint, either by having a heavier lift drone, or by if you're using a semi-airborne EM system where your receiver is much lighter, then I really don't see why you couldn't fly at 15 or 20 meters. You can't really fly these things at 20 meters per second, but generally at 15 to 18 meters per second range is kind of the max I've ever flown one of these multicopters. What I do think will happen is that the concept of putting these sensors into a fixed wing configuration, VTOL plane sort of thing, starts to make sense as well. So you can fly it faster. And I'm talking about semi-airborne EM configuration where you have a loop on the ground and you're flying back and forth. And I also think that the drone swarm concept will start to become something we're doing regularly as well. And one of the reasons for that is that partly it's data production, but it's also the idea of being able to have multiple transmitters out there that we're switching in between those transmitters. So we're actually flying the drones over, and then we're pulsing on one transmitter, and then for any of that position of those receivers, we're getting the ability to actually make sort of geospatial differential measurements of the EM field. And that to me could be pretty exciting in the future in terms of extracting more information about the subsurface.
Okay, a couple of more EM questions, and we'll maybe circle back if Timothy's online to answer Alistair's question about thermal imaging. Okay, can we use this method to identify cavities near the wells? Maybe you meant near like the pipe. So that was a question from Timur. Maybe if you want to pop on and just clarify if that was a question for Ron. So just raise your hand, and maybe if you want to pop on and clarify that, that'd be great. I'll just move on to the next question. You were thinking frequency domain like EM31 or 34.
Well,
okay, so that was in response to his previous comment.
I'm also been working with a system that is a frequency domain. It's a system called the GEM 2 UAV. It's made by a company in North Carolina called geofx, and it's multiple frequencies, fixed. It's a horizontal loop EM system. If you go to my website, you can see it where we're flying it over a field, a farmer's field. That actually is a very interesting system, and that in contrast to the 34, the 34 is a separated loop system, but the 31 is a fixed boom sort of system, and now I think Geonyx has an eight separations in their fixed boom. I think that's another approach to take. I think we'd be able to lift it. I think the reason Geonyx does a great job of making their ground-based systems extremely durable, as you can see from the picture I showed of the 61. But what we definitely need to, if we're going to do a fixed boom system, where I think you're talking about 3 meters of a bird that's hanging below a multicopter, that's going to require probably some engineering expertise that just to keep it stable. We can demonstrate that in a way, that's why I've gone to the GEM 2, is that because we're getting depth of investigation based on frequency of the signal versus based on distance between the receivers and the transmitter coils. So in a way, it's a lot easier to implement for a drone.
Hi, thank you. Yeah, this is Bob Grimm. Yeah, there's a lot of different ideas going around here that I think are kind of mixed up. My response earlier was just to the question about investigation depth first is usually comparable to the coil size. So you should be getting maybe 0.5 meter to 1 meter depth. And that's going to go down when you're in the air. So, pretty shallow. There was a question about using 2 separated coils, and that is rarely, if ever, used in time domain EM. You don't necessarily get more investigation depth by separating the coils. The most efficient thing you can do is to use a bigger coil, because the mass is best used as increasing the area of your coil. That gives you a bigger moment, and that'll increase your investigation depth. And there was also some confusion about the GEM. That's a frequency domain system, but frequency domain systems in that frequency band are using a fixed geometry like the EM 31 or 34, where your investigation depth increases with spacing. So if you did it's really like a DC resistivity survey in terms of how it works geometrically with sounding depth. So there's a lot of possibilities to do with drones. There are multi-drone ideas that maybe that would work in frequency domain, but the GEM, for example, does not increase its investigation depth with lower frequency. By having those multiple frequencies, you can get ground properties. You can get the spectrum of the EM response to the ground, but you do not get changes in investigation depth with it. So yeah, thanks for your talk. A lot of interesting things, but there's a whole world of Earth frequency and time domain geophysics that has to be kind of sorted through for how that works for drones.
Right. Yeah. And I still think EM and drones is relatively new. So this is, one of the first great concepts.
Definitely pioneering what Ron's done.
Yeah, thank you for clarifying some of that. That's awesome.
We have questions also in the chat, but keeping an eye out for hand raises. So that was so we have a question from Alex. Ron, great talk. It's always a pleasure to hear about what you have to show every year. Now, since payload capacity is such an issue, why not use a larger drone?
Money, cost, it's the drone I have. That's why. And do I want to use a larger drone? Yes, but one of the things that becomes evident after a while is that when you go a larger drone, you actually start increasing the degree of risk that's associated with flying those drones, and I'm going to say risk to people. Early on, and when I got into this, I was with a guy who had bought a larger drone, no, it wasn't any larger than the Matrice 600, but he had been used to flying a quadcopter. And when he got into the larger drone, it scared the heck out of him. And I didn't really fully understand why until I became a pilot myself. And what I saw was that the level of concern that you have over this thing that is much bigger and much more powerful increases exponentially. And so therefore you need to address the safety issues in a much different way than you would with, for example, a quadcopter. Okay, I see that. Can it be used to identify cavities near wells? This is, I assume you're talking about the EM61. And I think the answer to that is possibly, but it's not a conductivity mapper like the frequency domain systems are more they're used for mapping variations in conductivity. And as Bob Grin pointed out, that that there's a limited depth of exploration based on either the geometries or the frequencies you're using. And that's why the idea of having a fully contained time domain system starts to look pretty cool, pretty inspiring, but it's going to require having a larger dipole moment, which means a bigger loop. And when you go to that level, you're starting to get close to kind of things that are done in the helicopter domain with helicopter EM, time domain EM. So I believe there will be systems that will be built that will time domain EM systems that will be used to actually see much deeper, but not with the current drones that I use, and probably not until I'm going to kind of express an opinion here about until we get to BV loss, until that gets sorted out. Because once that gets sorted out, once the parameters for actually being able to occupy the airspace and fly beyond visual line of sight get sorted out, things like radio communication and sense and avoid and stuff like that, and what the regulators will agree to, then that'll open up a whole new domain for the use of drones that are much bigger and have much better lifting capacity. And what that, in my mind, means is that these time domain EM systems that will be built that'll approximate what you get now with a helicopter EM system. We'll get close to it.
Excellent. I'm just going to circle back. If Timothy, you're online, I think this question was for you from Alistair. How do we create orthomosaics from the thermal images? Is it difficult to match pixels?
So for the thermal stuff, actually, it's interesting. So you can do calibration measures both when you're taking off and landing to create these thermal masks. And actually, again, there's a paper that Jasper Bauer, who's the first author on, Bauer 2020. That'll be a remote sensing paper on looking at thermal data, but then also machine learning in terms of, again, the faster regional convolutional neural network stuff for the humanitarian demining. So like that paper describes exactly how to use a thermal mask to remove vignettes or cold corners from the images. And that actually helps to create a better ortho. The other things that you can do to create a better ortho are actually statistical. So what you're going to have during data collection is you're going to have problems in terms of like a flat field correction. So that means that so we're using uncooled thermal cameras, right? So the microbatometer like temperature is going to change through time. And what's going to happen is you'll have like one line of data where your values are up here at like, I don't know, say like the mean or like the median is like, I don't know, 23 degrees Celsius. But then the next line is going to be something different. And then the next line is going to be something different. So what you actually have to do is you actually have to either go through each image or each line of data, and you have to change it so they're statistically matched. And then what you can do is with thermocouples, match that to actual data on the ground so you have really accurate thermal data. Does that make sense? But yeah, there's kind of, it's not easy, but it's worth it in terms of going through and both collecting the data in a way that you can easily process it later, but also collecting the ground verification data that you can make sure that your accuracy is high. Thermal's tough. It's just tough, but it's totally worth it for this.
Awesome. Any reference to paper?
Oh
Jeff.
yeah, let me put that in the chat.
Yeah, I guess it's a good time we could put our contacts in the chat for those. Yeah, if any of the panelists or speakers want their contact information out there so people can contact you for more questions, please do put it in the chat.
We have a hand raised from Jeff.
Yeah, my question is for you, Timothy. Is there are there guidelines for hyperspectral drone flying? There's something our committee hasn't added to the list, but what I'm hearing from USGS and maybe from yourself, it's not straightforward. Are there guidelines, or are you working it out for yourself?
Yeah, so in terms of the hyperspectral, there's a number of issues. So you're going to get windowing problems, and the windowing problems are going to come from more or less. So we're collecting data and we're using a gimbal, right? And the gimbal is theoretically keeping our sensor, flat with respect to the ground at nadir, right? But that doesn't actually happen in the real world. And when you're using these push broom systems, right, which is what most of the systems are at this point, that are small enough and have low enough swap, size, weight, power requirements for a drone. That's pretty much what we're at. Those are the only ones that are under a kilogram. And so as it's moving its swath back and forth to collect the data, obviously it relies on motion. And because of that, if the motion is not at the right speed, at the right velocity, you're going to have data gaps, but also you're going to have problems with, like, is your IMU calibrated accurately? Which means, did you do the right turning maneuvers when you started your flight to calibrate it? But then it's not just that. So the longer your flight time, then the more that you're drifting your IMU, right? And your GPS data. So like you're losing, like, I don't know, 1/10 of a degree a minute if you're lucky, but it might be more. So you need to actually start to add extra GPS units so you can keep your heading errors to less than 1/10 of a degree. So there's a lot of stuff in terms of just like the data acquisition, but then when you're doing the processing is crazy too, right? Because you want to cut away all of, like, this is like, so hyperspectral is really similar to LiDAR in terms of data processing like this. You need to cut out a lot of the noisy data that exists at the beginning. So you need to create like some sort of metadata file that tells you that you're at the right altitude, and then clip all the data that's not, so that you're not processing data that's like flying up or doing your calibration measures or any of that type of stuff for your IMU. So like just straight up collecting good data, making sure that you're processing the right way. And then all of that is going to be really, really important. And then after that, then you start thinking about like payload considerations and things like that. So I've been moving slowly but surely from the M600 to more or less like gas electric hybrids. Like that's the future. So does that answer your question, or is there?
Well, it sounds like we need some guidelines written up from all that learning that you've done.
So what you're saying is we need to write a best practices paper.
Yeah, well, I think it'd be lovely if you could join the committee, the subcommittee on the hyperspectral. Yeah.
Sounds good. Yeah, I mean, I've been learning a lot about hyperspectral from the HABS project, and then also from UXO and things like that. So.
Yeah, thank you.
Great. We have another question came in, and I believe this is for Ron. Did you have some stability or data quality problem related to oscillation of the system? Filippo, I believe that's for Ron. If you want to jump on, if it's not, let me know.
Yeah, I think it. No, I didn't see any noise in the data due to the oscillations. We didn't really see much oscillations once it was moving forward. When we do the turnarounds, and then we, flying that slow was actually we found to be the real benefit of is that we didn't have a lot of movement, side by side movement of the payload. I've got to kind of reinforce what Jeff was saying is about we didn't specifically look at hyperspectral or spectral imaging as having a guideline for it, but we do believe that it needs to be included in the guidelines. We were just trying to address what we viewed as, or at least the committee is trying to address what it views as a real hole in helping people come up to speed. And, in terms of information, now people that have been flying these systems and have figured out and know something about geophysics and know good data from bad, they're not the ones who necessarily we're trying to address. What we're trying to do is help those that are getting into it. One of the early comments was the low price of entry into doing some of this drone-based geoscience. There's just a lot of folks that want to get into it that really don't have any background in doing the geoscience, either collection or interpretation, processing or whatever. And what we need is as a community to actually start. We're not going to stop the tide because the money's there. That's what's bringing the people in. What we need to do is collectively get together as a community and raise the quality of the data that's being acquired.
Great. There's a comment just from Bob. To reinforce Ron's response to motion or sway, this is one of the strengths of time domain EM because the measurement is made with the transmitter off and is relatively insensitive to geometric errors.
I had a question for Timothy, actually. I was wondering what some of the bigger challenges were of developing hyperspectral enabled drones. So, I mean, there was a lot of development moving forward from magnetics and things like that, but I was wondering if there's any specific details for developing, the hyperspectral sensors on drones. If you had any insight on that.
Hey, Callum, could you say that again? Sorry.
Yeah, no worries. I was just wondering what some of the bigger challenges were with developing hyperspectral enabled drones. Like there's a lot of kind of research and development that went into, MAG that I worked on to kind of prove that you can get some good quality data from this sort of thing. I was wondering what some of the challenges were specific to hyperspectral.
And yeah, I mean, I don't know if you're a vigorous self-promoter, but some of your papers on noise suppression in MAG are pretty awesome, by the way, just in case people don't know it. So
thank you.
I've definitely reviewed papers where I'm like, you should, like, it appears you haven't read this paper, you should look at it. So in terms of hyperspectral, the challenges are obviously, again, like getting high quality data that doesn't have windowing and all these other like noise artifacts. But once you've done that, that's cool. You've gone past like noisy artifacts, you've got high quality data. The problem is you have so much high quality data. You've got just like terabytes of high quality data. Like one of my students just stopped by and she's a rock star and she's working on UXO stuff. And she hands me this because she's been working on it. This is a 4 terabyte solid state drive. You know what I mean? And this barely handles the data that she's been working with.
Yeah.
Like, I mean, what do you do with that? Again, I have a network attached storage drive that has over 30 terabytes of data. Like then you start, when you're working on that level and you've got a NAS drive, you're then working about like pushing enough data, through what my university, let's be real, Science One, the building I'm in is the oldest science building on campus, the oldest building on campus. So just pushing data through that network actually slows down your data processing pipeline because the files are huge. So like a single file from the Corning Shark 410 instrument is 16 gigabytes. You process that like to do anything meaningful, and you're talking about, again, like quintupling your data size. Then and once you've done that and you've created your 155 bands of reflectance, then you have to start doing PCA because otherwise it's impossible to do anything with the data at this point. So yeah, we've moved definitely towards more of a kind of file size and those types of problems. Have you encountered any of that stuff, or is MAG still too ASCII and small for?
Well, with some of the stuff that I would work with the frequency domain and filtering signals and things like that, like if you'd be trying to run a fast Fourier transform on an entire data set or something like that, like good luck getting your computer even with 32 gigs of RAM that you just upgraded to be able to run all that. So you definitely have to like section it. So,
yeah, like my tough book. Yeah, same. Yeah. It's like, well, so yeah, do you do a lot of like power spectral densities to try to find out like instead of just like the kind of standard ways of looking at cyclicity of like noise and patterns, like I try to look at it like in a metric scale. So you can kind of, I don't know if you use much of that, but
yeah, a lot of the things that I ran on MATLAB were just trying to like basically look at what specific frequencies are in the data sets that you have, and then trying to characterize them with a bunch of the other metadata you have. So, I mean, a lot of fast Fourier transforms and just trying to, run out the window size of that transform as far as you can in the time domain. But then when you start doing that with something like the mag arrow at 1,000 hertz, and you're using the raw data for that, it's like you quickly just flood the RAM of your computer. So there's a lot of interesting challenges, I'd say, with the big data, even with the mag, if you're using the raw, like high-end things that I think are going to carry over with a lot of these bigger surveys that people run. But it's interesting.
Yeah, I mean, so I'm trying to think, when you work with like mag data, do you use like do you parse your data first? Because like, that's one of the things that I usually do right away is I just parse it so that it's easier to process. Or do you want to have all of that data so that you can see like, power line frequency noise and stuff? I don't know, what is Canada 50 or 60 hertz? I don't know. I can't remember, but
we're 60. Yeah.
60. Yeah. Like, so that you can, do you want to see that in your data, or do you want to just like parse that away, like right off the bat?
Depends on if I'm in like a production mode or if I'm more kind of the research. If I'm research, it's definitely like I'm trying to look at all the signals and kind of see what is coming from what, because you get all sorts of interesting signals that I haven't even been able to like quantify where they're coming from on the drones or things like that at specific frequencies, and it varies from drone to drone. So
from the rotors, yeah, exactly.
Yeah, and they're all over the place. But like, obviously, if I'm just going to be running like something to look at geology, you would definitely parse it right away down to something like 10 hertz, because it just becomes unbearable to kind of work with that. As long as you know what you're parsing away is not something that's going to be
not meaningful.
Yeah, exactly. And just a lot of the work that I had to do was, looking at that and verifying it and kind of proving it so that it was beyond a reasonable doubt.
Well, how fast are you usually flying? Oh, and that goes for you too, Ron, with mag.
Usually 10 meters per second seems to be what we tend to max out at with things like the M600 and stuff. Past that, you start to run into issues with the GPSs on the drones usually as well, because they tend to update you tend to run into update issues if you try and run any faster with the commercial systems like that. You need something a little bit more specialized. Obviously, we'd like to fly a lot faster, especially with the higher sampling frequency magnetometers and things like that. But yeah, it's again an interesting thing to look at for sure. How about you, Ron?
I'm just curious. Have you guys looked at much of the ambient noise in the mag data? Have you spent time trying to figure out where it's coming from?
The ambient noise in terms of like
power line noise. Generally, it's power line noise. So
yeah. The power line noise is interesting because it's almost like just a direct peak at that specific frequency. The UAV noise tends to be a lot more broader scale, just because the rotors kind of do,
because they move at different RPMs because of the Kalman filter to try to constantly fight the wind.
Yeah, exactly. So you get like this kind of band or hump around usually the rotor frequency, which tends to be around 45 to 50 hertz. So you can definitely tell the difference between the UAV signals and the power line signals for sure. Then you start getting some weird things as well, down around like 10 hertz. Sometimes you'll get signals in the data if you move the UAV closer to it, and 20 hertz, and it's kind of scratching your head. Well, what's this coming from?
Distance, from the UAV in terms of tethering. Yeah, for sure.
Yeah.
And then, have you all started doing any surveys near like wind energy, like wind farms? Like,
I have not myself.
They emit different frequency signals as well. So it's like
that's fun.
Yeah, well, it's kind of funny. Like the Fourier methods are like really good because you can figure out what it is in terms of its frequency content or in terms of its like cycle per meter content, and figure out like the distance that you have to be from things. It's pretty awesome. So that's more power spectral density stuff, but like, it's like there's a bunch of different ways to do this. So in terms of figuring out what the noise is and where the noise is coming from and how to cancel out the noise effectively. So
yeah, and I'm sure there'll be different applications of this as well for the EM systems that might come out as well, looking for that. So it's all kind of ties in together. Go ahead, Jeff.
Just to comment on the 50 hertz, we've used the GEM2 system quite extensively in the ground-based mode, and the power line monitor is actually quite interesting. We did a survey of an abandoned Italian prisoner of war camp in Australia, and we found that even though there was no active power connected to this old site, the power line monitor showed up beautifully the old plumbing system, the old water pipe system. So the water pipe system in the ground was picking up just the ambient 50 hertz noise. So it's a useful. I imagine if you actually had an earth system, if you're in an area where the water pipes are being used as an active earth, then I'd imagine the signal might even be stronger. You know, so. But it was essentially that the underground pipe system was being used like an aerial, a 50 hertz aerial, and then retransmitting back to the power line monitor of the GEM2.
Interesting.
Comment here, a common practice in ground-borne magnetic surveys is to sample at half the frequency of the local power grid. Thanks for that, Bruno. I know when I'm looking at MagGround data, I desample down to about 10 hertz. Just to look at big signature exploration type targets. So I guess depending on your use. Yeah, so Tim, thank you for posting your email again to everybody. That should work now. The to everybody function. Another comment, the full sample rate for some magnetometers say at 200 hertz is good for removing 60 hertz power line noise. Thanks for that, Ed. Okay, so you might not need that 1000 hertz if you want to look for power line noise. All right. Any final comments, Callum? Should we begin to wrap up?
Yeah, I don't have any other comments for today's session, sort of thing. Looking forward to tomorrow, where we are going to have magnetics, multi-sensor, and exploration, though. So very much looking forward to the talks we have lined up tomorrow.
Yeah. So it'll be a full day of technical talks. Great that the innovation panel was today, but that was just kind of an opener. Tomorrow's all technical talks and some keynotes. All right. Well, yeah, thanks again, everyone. Thanks, Ron, Timothy, and everyone else.
I'm going to say thank you guys for making this thing happen. You've done a great job of creating a really positive opening for the Summit on Drone Geophysics. Timothy or Tim, thanks for contributing your keynote. You're doing some real interesting work, as I think everybody that was online today should really look forward to the next couple days, 3 days, because if nothing else, what you guys are doing is you're presenting as much the state of where drones are for geoscience and remote sensing, and identifying some of the issues, which I'm kind of hoping that inspires some of the students that are out there watching to say they want to work on some of those problems. You know, I think there's a lot to be positive about the future of using airborne robotics, and the future of using. You can't deny the fact that we now live in a new age of electronics and new ways of sensing the world, the earth, and I just look forward to seeing what some very what unencumbered by experience folks come up with, because in a way that's what kind of constrains us, is sometimes our preconceived notions don't allow us to be a little bit more broader in thinking. So anyway, I want to thank you all for the opportunity, and Caleb and Laura, I really want to thank you for taking the helm and making this a successful start to the Summit on Drone Geophysics.
Great, thanks, Ron. And yeah, thank you everyone on the call. I just posted, I know some of the panelists are off the call now, so I know maybe reach out to myself or Lori or Callum, and we can connect you with them for email addresses. Because some of them didn't have time to stay on the whole day. So, yeah, that shouldn't be a problem. We'll just pass that information on to them for you. Yeah, because there's some great connections that can be made out of this, hopefully. So it's great. Thank you, everybody. We look forward to seeing you tomorrow. If you can join, same time.
Sure.
More great talks.
See you then. Thanks.
Thanks.
Bye.
Thank you, everyone.